Hello, very good morning to everyone, all the participants. I'm very excited to welcome you to day 2 of our GIAN course. So yesterday we had very exciting 3 lectures and 1 tutorial. So once again, I would like to invite our foreign expert, Dr. Ankur Jain, please.
Thank you so much. Thank you and welcome back, you all. Glad to see everybody's back. I thought I'll lose half the class, they'll run away and never come back after the first day. so good. Good to see everyone. Hope you all had a good rest and looking forward to a good day today. Yesterday we sort of started with some introduction stuff. We are going to make things deeper and deeper and somewhat more and more sophisticated as we pass. So please hang on, ask lots of questions, and let's have a good two-way discussion, dialogue, around the issue of lithium-ion batteries and thermal heat transfer in batteries and so on. Okay, so just to give you a reminder, this is an overview of our GIAN course. We are somewhere here right now. So today's first lecture, I will talk about thermal challenges in batteries. I will talk about all the things that can go wrong in a battery because of thermal related issues, and then I'll do some theoretical analysis of heat transfer in a battery, starting with steady state today and transient calculations tomorrow. And then Dr. Manish Agrawal will come back and he will continue his discussion of electrochemical modeling of batteries. In particular, he'll talk about the P2D model for battery modeling. It's a very popular, well-used model in the field of battery electrochemistry. And so actually I also look forward to learning from him because this is not something that I know very well. And at the end of the day, there will be a ANSYS simulations based tutorial where I will basically do a demo of a finite element simulation software tool that is used very commonly for solving heat transfer problems. Okay, and then next couple of days there will be lectures on measurements and interfacial heat transfer, a bunch of other things that we will talk about as we go forward. Okay, so let's get started. I can start here, I guess. So this is lecture number 4, and this is thermal challenges in batteries. The question is, what goes wrong if either the temperature is too high or the temperature is too low? That's what we're trying to learn here. In connection with that, I would like to point you to 2 very good papers. The first one is this paper by Todd Bendhauer from Georgia Tech. He was at Georgia Tech at that time. Now he is himself a professor at Colorado. In fact, this was the paper that I read casually in 2013 or 14 that led me to all my interest in batteries. Until then, I didn't know what batteries are. My PhD and my training during PhD and afterwards was on a very different topic, semiconductor thermal management. I got to know about batteries mainly from this paper in 2013 or 14, and this is an excellent paper. I would strongly recommend you all to read it from start to finish. It's a very comprehensive paper, but it tells you a lot of useful things. Critical review of thermal issues in lithium-ion batteries. When we read papers, oftentimes papers are written in a way that are very difficult to understand because they don't tell you the full story, right? They don't tell you the small little tricks, tricks of the trade. This paper does a very good job of laying it all out in front of you, right? He does not hold back. He tells you about anything and everything that he knows about thermal issues in batteries. Okay, I happened to meet him at a conference afterwards. I shook his hands. I said, "Thank you so much. This is indeed the paper that sort of launched my own independent career in a way, right?" And he looks at me and says, "Yeah, that's a good paper. It's getting a lot of citations, but you know what? It was a pain to write." he said it very genuinely. He said it was very, very painful to write. And I can see why, because, you know, you look at you look at just the second page and he has all this data that he is summarizing 20 other papers. So he has read 20 other papers and he's summarizing what all other people have done in the community, and he's putting it out there for somebody like us to read, right? It's an excellent service to the community, and it really genuinely is an excellent paper. Okay, so if you are interested in this field, I think this is the first place that you should go to. Read this paper from start to finish. Read it again. It takes a couple of times. Make your own notes on the sidelines and all that. Takes a few minutes, I mean a few iterations for you to truly understand what is going on. Okay. The only drawback that I would say of this paper is that now it's a somewhat old paper. Now it's about 13-14 years old. So it obviously will not catch the more recent things that have happened in the community, right? For that, I will also point out a few other papers that I would recommend. But this one, just to go through it, it talks about thermal effects in lithium-ion batteries. Let me zoom out a little bit so that it is easier to see. Yep. So it talks about thermal effects in lithium-ion batteries, where it talks about all the things that can go wrong: self-discharge, capacity fade, etc. And it talks about all the different other papers that have worked on those subfields. It talks about the nature of heat transfer in batteries. How does heat get generated? Why does a battery generate heat? What happens to that heat as after it is generated? How is it removed? And so on and so forth. And it's a world of very good knowledge to start with. Okay, so I'll stop this here. This is the paper that you should be reading: Bendhauer, Garimella, and Tom Fuller, and an excellent paper. Okay, so today's seminar, this lecture will roughly be based on some of the concepts that Todd talks about in his paper, and we'll go from there. In addition to this, there is a paper that some of my students wrote a few years ago, which is also a good one to read. So this is thermal management of batteries for improved safety and performance. So Todd Bendhauer's paper was somewhat more fundamental in nature, in the sense that he talks about the heat transfer processes that happen in a battery, right? Ever since then, the community has learned that it becomes important to remove heat from a lithium ion cell or a battery pack, and people have come up with all kinds of different thermal management techniques for lithium ion batteries, whether it is air cooling or liquid cooling or heat pipes or phase change materials or what have you. The community as a whole has literally thrown anything and everything they know at the question of cooling of a battery pack. So the area of thermal management of battery packs has come up very much in the last 10 years or so, and it's still a very active research field. And this paper that we wrote a couple of years ago summarizes specifically thermal management of lithium ion cells. How do you cool lithium ion cells in battery packs? Do you immerse it in a coolant? Do you place a heat pipe in it? Do you surround it with the phase change material? And so on and so forth. Those are the issues that we summarized in this paper. This is from the annual reviews of heat transfer, ARHT. So I would also strongly recommend that you read this paper as well. This is a more recent paper. And while we are at it, I can also show one more extremely recent paper, just a few weeks ago, in fact. I don't know if I have a PDF of it here. I don't have a PDF of it here. I'll talk about it maybe separately in the next lecture. Anyway, so for now, it is this paper by Dhananjay Mishra. And this other paper by Todd Bendhauer. Those are the two papers I would recommend. Okay. By the way, Dhananjay Mishra is a very interesting character. He comes from Dehradun. He did his bachelor's degree there, came to UT Arlington, did his master's with me, and then he said, Dr. Jain, I want to do a PhD. And he went through a lot of difficult times at the start. I will discuss probably tomorrow or the day after some of the problems that he came up with and he wanted to address. I was myself new in that field at that time, and it took him a lot of time to get going. It was a very long period where he was trying this and trying that and nothing was working out, and he was learning a lot along the way, but there was no output for a significant amount of time. Okay. And I really am appreciative of his patience and his consistency and his sort of his ability to hang in there. Sometimes when things don't go right, you just have to hang in there and let the storm pass, and just keep going, and just not totally give up. If you totally give up, it's never going to happen. But if you somehow hang in there, things can turn around, and good days will come, right? So for me, he's a shining example of that persistence. He finished up at the end when he finished his PhD. He had like 6 or 7 excellent papers, very high quality work that the industry really loved and liked, and he had 2 very good job offers by the time he finished his PhD. He works for General Motors now, and he does battery thermal management for General Motors. So, the electric cars of the future he'll probably have some small role to play in the thermal management of General Motor cars in the future. Okay. And I'm saying this because I know from personal experience as a PhD student myself, and also having seen my students, that doing a PhD is not straightforward, right? It's not like going to classes, taking exams and finishing, right? It takes a lot of time and effort to identify the problem you want to work on, to identify the methods that you will use, and then actually do the work and then publish it and all the other stuff that goes on in doing a PhD, right? So it is as much a test of your technical expertise as it is a test of your resolve, your character, your ability to solve very difficult problems, your ability to persist out there. Okay, all right. So with that, let me go and let's start talking about what are the thermal challenges in a lithium-ion battery. Yesterday, I had shown a very simple schematic of a battery. It had an electrolyte, a liquid electrolyte, and it had 2 electrodes, and it had a salt bridge, and these 2 were connected to each other through an external medium, right? So imagine 2 jars filled of a liquid and 2 metal strips sitting in the jar, and the 2 connecting to each other through an external circuit, right? It would be impossible to have something like that and carry it with me along with my laptop or my cell phone device, right? So this is the conceptual idea of a battery, but the practical real life implementation of this idea looks very different. So in a typical lithium ion battery, for example, what happens is that we take several sheets of material, and let me use different colors here, that would be very helpful. How many do I need? I need 5 of them. So let's keep going. And finally, the last one can be black again. So what these sheets are current collector, both of them. The red one is anode, the green one is cathode, and the orange one is separator. So instead of having these strips for the anode and cathode, we take the anode and cathode material and we lay it out on a thin sheet. Almost like take a piece of paper and paint the material on it. Typically the cathode is made up of a lithium salt such as lithium cobalt oxide. So we take lithium cobalt oxide, we basically grind it, and then we also add some binders, inactive binders, and basically create a slurry. And that slurry is almost painted on some kind of a porous base. And that is how we create a very thin sheet of the cathode material. That thin sheet literally looks like a piece of paper. It is as thin as a piece of paper. Okay? The anode is typically made up of carbon, graphite in particular. Okay? And the separator is typically made up of polymers such as polypropylene. So you take these different sheets, and of course the current collectors are the ones which will collect the current and which will route it out to the external load. Those current collectors are obviously made up of a metal such as aluminum or copper. Those are the two most commonly used materials for the current collector. Now, having taken all these sheets together, in order to build a battery, I will take all those sheets, put them next to each other, right? And that essentially creates a battery. The one thing missing here is the electrolyte. I don't have the electrolyte yet. So what I will do is that I will take this stack of paper, sort of, and I will put it in a casing. So suppose I have a casing like this, typically made up of metal. I will take these sheets which will, this stack will now look like this, right? I will put it into the casing and I will pour electrolyte into it. The electrolyte is very important. That is how the lithium ions will travel. Right? That is how the lithium ions will travel. The separator is also important because the separator basically ensures that the lithium ions are able to move through it, but it stops the electrons from traveling across. Because the electrons are supposed to go outside the circuit so that I can light a light bulb, or I can run a fan, or whatever it is, run an electric car that is going, right? So the separator plays an important role. And the electrolyte, when I put the electrolyte, this thing is submerged in the electrolyte, and then I can seal it off. Right? I need to take care of a few things, however. The first thing is, before I seal it off, I need to be able to make connections. Correct? So typically what is done is that one end, this end of the current collector is connected to the body of the casing, and the other end, the other current collector on the other end of the stack is connected to the cap. So this is the cap and this is the casing. In order for me to be able to make an electrical connection. So essentially, as a result of that, the cap becomes the positive terminal and the casing becomes the negative terminal. Correct? Everyone with me so far? Question? Yes.
The seed, sir, is it really put means anodes or anode and cathode are made of the seed, or it's just a spray coating on the current collector?
No, it is not a coating on the current collector. They are independent sheets of paper. Imagine I have a black colored sheet, which is the current collector. I have separately a red colored paper, which is the anode. It's not just directly spray coated on the current collector. They need to be manufactured separately, right? So in fact, in the end, what happens is that each of these come in a roll. Think of a toilet paper roll, right? As you pull it out, you get the paper coming out, right? Each of these comes in a roll, and then I have these rolls coming together, and there is a machine that presses them together in order to create like a composite paper containing 5 different layers, right? And it is that paper, the thing here, that has, for clarity, let me just show a red color and a orange color and a green color. So this is the composite here, which is then put inside. Do you see what I'm saying? Cool. Any other questions or comments so far?
So we were thinking about it has been made as a layer. Are they using any melt spun technique?
I don't know the answer to that. No, I'm not sure.
So what would be the isostatic pressure they are applying?
Quite a lot. I don't know the numbers, but these are compressed very heavily.
That's what I'm asking, because we are adding some granular agents, binders.
Yes.
To get fixed with the surface.
Correct.
When we are having a void or any kind of defects originating when we are pressing these things, it might also leads to create some surface interface disturbances.
Yes. Absolutely. Absolutely. Yes, exactly. So, the manufacturing of a lithium ion cell is itself a topic of its own. Okay. And those who are very familiar with the manufacturing can give you a 2-hour lecture on how this entire process works. Right? Keep in mind that when I put the cap on the casing, I don't want the two of them to come in electrical contact with each other. Do you see what I'm saying? The plus and the minus need to be isolated. So for that, what actually happens is that you put a plastic ring around the casing before you put the metal cap. Are you able to visualize this? I have a casing, I put a O-ring sort of a thing, and then I put the cap. So the plus and the minus terminals are separated only by this tiny little plastic ring. That plastic ring has a very important role to play. Right? If that plastic ring fails, then the thing will short and all kinds of things will go wrong. And the way this is made, this essentially becomes a prismatic lithium ion cell. Oh, I want to see if I can do something about this. Okay, never mind. We'll just have to live with what we have. I do want to increase the size a little bit. Okay, we are back. This is a prismatic cell, which is, typically the cells that go into cell phones and things like that, flat, like a thin flat box. The way I have shown it, it is a 1-layer cell, right? I just have 5 layers of material. Each of these are very thin. What is the typical thickness of a piece of paper? How thick is paper? How many microns? Sorry? Even less, about 100 micron thick. So if I take 5 of them together, this thing is less than 1 millimeter thick total, right? That will not store a lot of energy. In order to be able to store more energy, what we do is that we fold it like this. Very tightly, of course, not as loosely as I have shown here. It is folded extremely tightly. Sort of like if you have been to if you've been to a shop to buy cloth to stitch a shirt or something like that, they fold the fabric like this, right? That is exactly how it happens to create a prismatic cell. Sometimes it is also of interest to build a cylindrical cell. And to build a cylindrical cell, what we do is that we take a thin metal pipe, tube, it's called a mandrel. And we wrap this composite sheet around this mandrel, right? To create what looks like a roll of toilet paper. It literally looks like toilet paper, right? Except that this mandrel is very, very thin. So if I look at it from the top, I would have the mandrel and I would have my sheet going around it, wound very tightly. I'll wind it as tightly as I can so that I can compress it and I can put as much material as I can in the same limited space. And after I have done this winding, I will take a metal can and I'll do the same thing. I will insert my roll. This is often called a jelly roll. I'll insert my jelly roll and then I will place my cap on top. Again, I will need the plastic ring in order to separate the two. There are a couple of other very interesting features around this cap. So if I was to zoom into this region, this region has two features. It has a safety valve, a pressure valve. Oh, pressure valve. Why do we need a pressure valve? We need a pressure valve because, remember, in addition to the jelly roll, this also has the electrolyte in it. So this entire thing is submerged in electrolyte. The electrolyte is typically an organic solvent. It's an organic solvent which is close to acetone. It is not quite acetone, but chemically it is close to acetone. It actually is a mixture of a lot of things. Ethyl carbamate and EC, MEC, diethyl, DEC, etc. Yes. Exactly, yes. So it's a fairly complicated chemical mixture. From a heat transfer point of view or from a practical point of view, all we need to know is that one, it is highly combustible and two, it is highly volatile, which means that while I inserted it in as a liquid, if the battery gets too hot, that liquid will begin to vaporize, and as it vaporizes, the pressure inside this sealed battery will begin to rise, and therefore I need a pressure relief valve so that if the pressure becomes too high, then instead of having the battery completely explode, I hope to be able to release some of the electrolyte outside. and perhaps be able to save the cell. Okay. There is a lot of research on non-volatile, non-combustible electrolytes that is going on, but for now the state of the art in the world of lithium-ion batteries is a highly dangerous combustible volatile electrolyte which causes its own problems. Imagine if imagine, people think of all kinds of worst case scenarios in this area, right? What is the worst thing that could happen to an electric vehicle where we may need to worry about the safety of the battery pack? It gets into an accident, right? Or it catches fire for whatever reason. And then this, this battery contains very dangerous electrolyte that can catch fire, right? It's not going to catch fire until it comes out of the battery. Until then it is safe. But if this battery ruptures, say the car goes and hits something and something ruptures this cell, or if the pressure inside goes too high and it explodes because the material of the metal can only withstand as much pressure, right? Now you can take a step back and say, okay, I can make my metal can thicker in order to be able to withstand that pressure. But in doing so, you will increase the weight of your system. And then your car will become heavier and the efficiency of the car will go down and so on and so forth. Right? So at any rate, when the pressure inside reaches the limits of the metal can, it is liable to exploding. A mechanical failure will occur. It will crack or rupture, and all this volatile electrolyte sitting inside at high temperature will come out. And there is probably a fire around. This electric car has gotten into an accident. There's a small fire, right? You will be adding fuel to fire. So something similar happens in IC engines also, by the way, right? An IC engine car also carries several liters of fuel with it, which will add to the fire in case of an accident. Unfortunately, the same thing also happens in an electric car. The electric car also carries with it volatile combustible electrolyte. So the pressure valve is one safety feature that is built into the cap of the cell. The other very common safety feature is called I forget the name of this thing. I'll go back and take a look at it and make sure I give you the right word. But what it is basically a resistor switch. And again, I don't know the electronics of it. All that it does is that if the current through that element exceeds a certain limit, it basically opens a switch. I don't know what it is, honestly. Yeah, so it's possibly some such electronic component whose function is simply that, look, if there is a short circuit and if there is too much current going out of the cell, remember yesterday we learned that Q triple prime was roughly I square R, which means that the higher the current, the greater would be the heat generation rate, right? I need to be able to limit the discharge rate of this cell to a certain value. If it exceeds that current, there would be simply too much heat generation occurring, and that will cause a problem. So I also have another safety feature here, which is sort of like a resistance switch, which will shut off power to the cell or out of the cell if the current is too much. Okay. In addition to that, the separator also has a bunch of safety features built into it. The separator, as I said in the previous slide, is built out of a very porous plastic such as polypropylene. So if I look at the structure of the separator, it is sort of like a woven mat. This is roughly what the separator would look like. And you can design the separator in a way that if the separator gets too hot, then the material of the separator could melt and as it melts, it will basically fill up these pores, and it will slow down or stop the transfer of lithium ions through the pores of the separator. So that is yet another safety feature built into most lithium ion cells. Okay? Really, we are all designing this in terms of a worst case scenario. We have to think of all the bad things that can happen to a lithium ion cell and try to prevent that through a bunch of these safety features. Okay? Now, having understood the structure of a typical lithium ion cell, let's start talking about what are all the bad things that happen with a lithium ion cell at elevated temperatures. So we have to worry about two things here. So the first is thermal effects at high temperature, and very briefly I'll also talk about thermal effects at low temperature. So as the temperature of the cell goes up, a few bad things happen which affect its performance and safety. Remember in the previous lecture, yesterday's lecture, we talked about the different performance parameters of an energy storage device. How many watt hours of energy can it store per kilogram? How many watts of output can it give per kilogram, and so on. It turns out that at higher temperatures, all of those performance parameters are negatively affected. In other words, the capacity of the cell fades away. If the cell originally was capable of storing 1000 watt hours of energy, then at a higher temperature it might only be able to store 850 watt hours of energy. Okay, I don't think I want to get into the details of why this happens. I just want you to be aware of these effects. So at elevated temperatures, capacity fade occurs, because of which the cell will be capable of storing less energy. That is the reason why an electric vehicle has a reduced range as the temperature goes up. Any one of you have an electric scooter by any chance? Have you experienced this? What is the percentage reduction, roughly speaking, in the range going between spring and peak summer? 15-20% less? Yeah, that is quite typical. That is quite typical. So the same electric vehicle, whether car or scooter, that was able to go up to 150 kilometers in the spring on a full charge will now only be able to go 120 kilometers in the peak of summer. That capacity will recover to some extent. Yes. So to some extent the idea of capacity fade is a reversible thing, but that is a topic of current research. People are trying to understand the mechanisms of capacity fade, and through a bunch of experiments try to understand whether it is reversible, and if so, how many times can you abuse the cell before it really gives up on you, right? Probably the first time it will be reversible, it will be okay to come back, right? But if you do it enough number of times, then at some point it says, what are you doing to me? Just let me go. And at some point the capacity of the cell will irreversibly reduce. Okay, so capacity fade occurs because of high temperature, right? And this high temperature could be because of two reasons. The high temperature could occur because of charge or discharge at high temperature. Okay, so you run your car or electric scooter in the summer when it is very hot, and because of that the capacity of the cell goes down. The other reason why the capacity could fade is because of high temperature storage. Even if you're not running your scooter, even if it is sitting out there in the sun at very high temperatures, that itself will cause a reduction in its capacity. And this is usually not a reversible effect. In fact, you've probably experienced this. If you take a AA cell, if you put it somewhere and forget about it, and you find it 5 years later, it doesn't work as well anymore. In other words, all of these cells have a tendency to discharge by themselves, even when you have not connected them to an external load. The charge stored inside will find a way of escaping. It happens very slowly at room temperature, so that a AA battery can be stored for several years before it completely discharges, right? But if you do the same thing at a higher temperature, if you put your AA battery out in the sun and just leave it there, it will discharge much faster. The reason for that is that all of these processes are essentially chemical decomposition reactions. There are decomposition processes occurring inside the cell, irreversible decomposition reactions that inevitably are functions of temperature, right? Almost all chemical reactions, as you all know, the rate of chemical reactions depends on temperature. So if I have any chemical reaction, let's say I guess I can take any reaction, HCl I can't think of a good reaction to give right now, but let's just say, take a very simple reaction. This producing NaCl plus H2O, the rate of this reaction is known to be temperature dependent. In fact, if you look at the field of chemical kinetics, the rate of reaction as a function of temperature, what does this curve look like? Will it go up or down? It will go up. It will in fact go up very non-linearly. It's an extremely non-linear curve. I guess the simplest example of this that you all can perhaps relate to is food. If you cook food and leave it out there, it will go bad in a few hours in the summer, right? Whereas in the winters, it will stay for much longer. And if you put it in the refrigerator, it will stay for several days. And if you put it in the freezer, it will stay there for several months, right? That essentially is this curve. That the rate of the reactions that occur, that cause the food to go bad, goes up very dramatically with temperature. Similarly, the decomposition reactions that occur inside the cell that cause its capacity to fade over time are also accelerated by temperature. In fact, the rule of thumb is every 10 degrees Celsius increase in temperature doubles the rate of a chemical reaction. So 30 degrees C versus 60 degrees C, 2 times 4 times 8, 248, right? Roughly the rate of this capacity fade will be 8 times greater at 60 degrees C compared to 30 degrees C. Okay? Any questions? Yes. 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 The reversible loss? I don't know, honestly. No, I don't have a good feel for that. But clearly there is some reversibility. The electric vehicle that performs poorly in the summer does come back a little bit. It may never come back to its original, but it does come back somewhat, right? But no, sorry, I don't know the mechanisms behind it. Okay. So by the way, what Dr. Agarwal was referring to, lithium plating and SEI growth, etc. What happens in a cell is that there is this main reaction that we talked about yesterday, where the lithium ions combine with, say, graphite and intercalate on the anode side or on the cathode side and so on. That is the main reaction. And that reaction is reversible for several cycles. But in addition to that main reaction, there are also a number of side reactions that occur inside a lithium ion cell, which basically consume the lithium. So, for example, lithium plating that occurs on one of the electrodes is basically a process in which some of the lithium that is inside the cell is used up, it's sort of locked away in a plating reaction, because of which it is no longer available for participating in the energy storage process, right? And that is what is responsible for the irreversible capacity loss during the operation of a lithium ion cell. That plating reaction is something that inevitably occurs, and a high temperature essentially accelerates that reaction. It will happen at a higher and higher speed as the temperature goes up.
This capacity fade is generally occurring because of the rate of increase in the side reaction.
Exactly. Yes, those side reactions that consume the lithium will basically take a big chunk out of the available lithium, and you will no longer have the full lithium available for energy storage. This can be, yes, you can call it the loss of active material. Yes. Okay, any other questions so far? In addition to capacity fade, the other phenomena that happens is called power fade, which means that the power that you can get out of a cell, joules per second, also goes down. So in the context of an electric car, what that means is that the available charge in the car goes down because of capacity fade, but in addition to that, how fast can you get that charge out of the car also reduces. In other words, you can no longer accelerate your car as fast as you could have otherwise, right? So, and power fade is it's a little bit of a, it's less, it's not as easy to perceive as capacity fade is. It's a sort of a weaker phenomenon. Capacity fade is very clear, it happens very clearly. Power fade also happens, but not as strongly as capacity fade does. So capacity fade in some sense is like joules. How many joules are you able to store, right? Power fade is sort of like joules per second. How fast can you put charge into the battery or get charge out of the battery? Okay. So there's capacity fade, there is power fade, and then there is self-discharge. Which basically is the phenomena of the cell losing its capacity by itself even if you have not connected it. And that process is accelerated at higher temperatures. At higher temperatures, it will lose its ability very quickly. Okay? Unfortunately, I myself am not very familiar with the mechanisms underneath these phenomena, but I would direct you to the paper by Todd Bentauer. That has some details, but more importantly, it has references to papers that go into the deep details of each of these processes, including experiments. A lot of this is empirical in nature, right? People know that capacity fade occurs, but people don't really know the exact mechanisms behind it and how it all works, the questions of reversibility versus irreversibility, the questions of cyclability versus, in other words, if I expose the cell to 80 degrees C for 2 hours versus if I expose it to 80 degrees for half an hour, bring it back, 80 degrees for half an hour, bring it back. In other words, if I cycle it over temperature, how does the effect change between these two? Those are all open questions in the community, and a lot of the times people just take an empirical approach to it. Let's just try it out and see what happens, instead of being able to predict it using the fundamental equations. And what that means is that much of it also becomes a function of the chemistry of the cell, right? Depending on the cell chemistry, the capacity fade and other processes could vary from a lithium cobalt oxide cell versus a lithium iron phosphate cell, and so on. It could also depend on the SOC of the cell, the state of charge. How much charge does it currently have can also change things, right? So it's a fairly active, open area of research, not only to understand the fundamental mechanisms behind these processes, but also to be able to predict it through, just experiments. Let's just test it out and see what happens. So very commonly, the very common equipment that is used for these experiments is called an environment chamber. So it is simply a box with a heater inside it, or if you want to do low temperature experiments, then some kind of a refrigerant cooler inside it, with which you can maintain the temperature inside the box at a certain temperature, right? And the experiments are actually very simple. You take 5 cells, you stick them inside, you start a clock, and come back after a certain amount of time, withdraw one cell, measure its capacity. Then after 2 more days or 2 more months, take out another cell, measure its capacity, and so on, right? So it may not satisfy somebody who wants to understand the fundamentals of the process, but it certainly gives you a trend of what to expect. Most companies will run such measurements in a lot of detail for them to be able to understand the life of their battery packs that go into electric cars and electric scooters. Okay, so quite likely, after doing a lot of math and a lot of theory, you finish with your PhD, go work for a company like General Motors, you will end up doing simple experiments like this. I'm not trying to undermine the importance of those experiments, but oftentimes they might come across as being very simple experiments to you, and that's quite okay. In doing a PhD, you all are learning to solve the most difficult problems, and once you have the confidence and the ability to solve very difficult problems, you can go out there and do anything that you want, right? I want the process of doing a PhD to give you that kind of confidence that, look, now having solved this extremely difficult problem, I can go out there and I can solve any problem that the world can throw at me. Yeah, good. All right. So this is sort of my discussion related to performance. I want to talk about safety now. So safety challenges. Mostly at high temperature. Much of our discussion will focus on high temperature problems. At the end of this lecture, I will very briefly talk about low temperature problems as well, because there are problems when the temperature of the cell goes too low as well. So at high temperatures, there are some very severe safety problems that occur in a lithium ion cell. I was referring to it a few slides ago, where we were talking about the electrolyte. So this construction of a lithium ion cell can undergo several problems at high temperatures. Basically, the idea that those irreversible side reactions that we were talking about, lithium plating, let me write this down. And actually even before that, SEI decomposition, let me explain what this means. So what happens in a cell is that during the first few cycles of charge and discharge, there is a very thin passivation layer that grows on one of the electrodes, which basically protects that electrode from the electrolyte. The corrosive electrolyte inside can actually eat away the electrode, and that is why, and basically a very thin layer, a passivation layer on the top grows, which happens to protect the rest of the the electrode. The very simple example that I can give is that of aluminum. So if you take a freshly manufactured sheet of aluminum, it looks extremely shiny. But if you leave it out there in the air, very soon there is a very thin, in a different color, aluminum oxide layer formed at the top, which makes the surface very dull, right? But the good thing is that this aluminum oxide layer, even a very thin aluminum oxide layer, will protect the rest of the aluminum from corroding, because the transport of oxygen through this aluminum oxide layer is very slow. So even a thin layer of aluminum oxide protects aluminum. Something very similar happens inside a cell. The layer, the passivation layer is called SEI, solid electrolyte interface, and that layer plays a very important role in keeping the cell healthy. However, at high temperatures, the first bad thing that happens is that that layer begins to decompose. And that is simply because of how life is. Chemical reactions occur faster at higher temperatures. So the SEI layer does decompose even at room temperature, but it will take years to decompose because the reaction is so slow. As the temperature goes up, those reactions occur faster and faster, because of which the SEI will decompose faster and faster. And at some point, that protective layer on the electrode will break down, and that electrode will now be exposed to the electrolyte. This process, it turns out, generates some heat. It's an exothermic process. And the problem is that the heat generated by this exothermic process will increase the temperature of the cell even more. But if the temperature of the cell rises even more, the rate of that reaction will rise even more. If the rate of that reaction rises even more, it generates even more heat, which causes even more temperature rise, which causes even more heat generation, which causes even more temperature rise, and you can see that this is a positive feedback loop, right? It's sort of like the more I eat, the hungrier I get. If that happens, then I'm in deep trouble, because I'll get hungry, I will eat, but if I eat, I get even more hungry, so I'll eat even more, and eventually I'll just explode. Fortunately, all of us, unless you're not well or whatever, have a negative feedback going, that the more you eat, the less hungry you feel, right? And therefore, nature has a way of limiting how much we eat. All is good. But there are some scenarios where processes occur in a positive feedback loop. And this is one such example. More heat generation causes more temperature rise, which causes even more heat generation, and the thing sort of loops around until the temperature is so high that the whole thing will just explode. More specifically, what happens inside a lithium ion cell is that once the heat generated by the SEI decomposition causes a certain temperature rise, which activates the reaction between electrodes and electrolyte. the heat generated by these reactions further activates the decomposition of the electrolyte, which further provides the fuel to activate the combustion of the electrolyte. You see, these reactions occur at a fairly high temperature. These reactions would never occur if the first reaction happens, right? So essentially the first reaction provides the fuel to activate the second reaction, which provides the fuel to activate the third reaction, which provides the fuel to activate the fourth reaction. And you can see that this is very different from capacity fade or power fade or whatever, right? If you have capacity fade occurring because the temperature is too high, sure, your electric scooter will only go 120 kilometers instead of 150, but it will go, right? Here, on the other hand, this is a much more dramatic, catastrophic failure. The heat generated in these decomposition reactions is so high that the temperature of the cell will go extremely high, the metal casing will melt or will decompose, will rupture because of the increased pressure, things will catch fire, and eventually the entire battery pack catches fire. Right? You've probably seen YouTube videos of lithium ion batteries catching fire. This is what happens that is behind all those dramatic videos. This process is called thermal runaway. Thermal runaway is what is responsible for a bunch of accidents that have happened on a related to electric vehicles, aircraft, cell phone. Cell phone devices like Galaxy Note 7, not Galaxy, just Notes.
Redmi.
Huh?
Redmi. The Xiaomi.
Really? Okay. No.
They are having yes,
Sorry.
Samsung also.
Samsung Note 7. Yes.
Also,
Yeah.
and Xiaomi.
Yeah.
Also having some thermal issues.
Exactly. All kinds of problems occur, and as a manufacturer, you have to be very cognizant of something like this, right? If 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 a cell phone catches fire in the hands of your consumer, and if the consumer gets burned, that's not good for your brand, right? We are talking here about literally billions of dollars of potential losses for a company if something like this happens. And therefore, all these companies, Xiaomi and Samsung, etc., they have to be very careful in the design of their battery systems in order to prevent thermal runaway. Unfortunately, this process is very difficult to control once it begins. If SEI decomposition happens, and it is then that you wake up and realize something is wrong and I need to cool things down, by then it is usually too late. By then this thing is generating enough heat that eventually the electrodes and electrolyte will begin to decompose, and then it's like a train coming down the hill. There's nothing you can do about it. You cannot stop it anymore, right? So a lot of research on thermal runaway has focused on preemptive prediction or prevention of thermal runaway. What can you do in advance to be able to say that, look, I am at risk and I need to cool things down, I need to shut down my cell. There are 5 other things that I can do in order to try and prevent thermal runaway from occurring. Yes? Yes.
And I know that like from the empirical relationship or from the environmental
Yes.
at which temperature there is, and as soon as the temperature reaches, I just shut down the battery.
Sure. Yeah. Or you can conservatively say that, look, if 60 degrees C is my limit, I'll shut down at 50 degrees C. Or alternately, I can say that not only will I measure the temperature, but I will also measure the rate of increase of temperature. So even if I am at 40 degrees C, but my temperature is rising too fast, then that tells me to shut things down. Sure, fair enough. But the problem is that a lithium ion battery is a hermetically sealed system. Where will I place a thermocouple or some other sensor in order to measure the temperature? I can only place it on the outside. I cannot drill a hole into it and insert a thermocouple inside. I can maybe ask the manufacturer to please put a thermocouple inside during the manufacturing process, but that does not go very well because the manufacturer says, you know what, this thermocouple inside and the two wires that are coming out of it is too much trouble for me, and it changes the reliability of the cell, the cost, this, that, and an electric vehicle has 10,000 cells. Are you really going to put 10,000 thermocouples into it? You really cannot. Even if the thermocouple costs $1 per thermocouple, which is very conservative, you're looking at $10,000 just for the thermocouple, not even the batteries, right? That's not going to fly. So the only place where you have availability is on the outside of the cell. And the problem is that the thermal conductivity inside the cell, the thermal resistance, let's talk in terms of thermal resistance. The thermal resistance inside the cell is so large that there is a significant temperature difference between the outside and the inside. When the outside shows 60 degrees C, the inside could very well already be at 120 degrees C, and then it would be too late for you to do something. Okay. Now to that you could make a counter argument and say, okay, why can I not make a correction to it? Right? If I know this temperature difference, then I can account for it in my temperature measurements. That certainly can be done. We have papers on it which derive expressions for this temperature difference as a function of the geometry of the cell and the thermal conductivity of the cell and so on, based on which we are able to say that, look, this is the kind of temperature difference that we expect to see in a cell, based on which you can go and correct it if you want. That's a well established fact, and our lab, for example, has shown how this temperature difference depends on various parameters of the cell. Yes, we are. So we are heterogeneous heat generation? No. We are assuming the entire cell to be a homogeneous body generating heat uniformly throughout the volume of the cell. Right? So keep in mind that a lot of the times when we do thermal modeling, we'll talk about thermal modeling in the next lecture. When we do thermal modeling, we neglect the fine features of the cell. Right? If you look deep inside, this has many features. Right? The cell itself may be a few centimeters in diameter, but the components of the cell are only 10-50-ish microns in dimensions. Modeling such a multi-scale problem is challenging, and oftentimes you will find that people neglect the details on the jelly roll of the cell and they assume the entire cell to be a homogeneous body. Okay, so this is a good topic, and perhaps I'll talk more about this in one of the tutorials. For now, maybe I can just very quickly show that paper and the basic technique that we used. So let me see if I can find it real quick. It was several years ago. I am looking for Parhizi. Almost there. Here, determination of the core temperature of a lithium ion cell during thermal runaway. The argument we make here is exactly what we were talking about, that the surface temperature measurement of a cell is not reliable. It does not really tell me the full picture of the temperature field inside the cell. The key conclusion is right here. The core temperature is found to exceed surface temperature by hundreds of degrees Celsius. So if your core temperature is saying sorry, if your surface temperature says that the cell is at 100 degrees C and you think you're in trouble, you're in fact in deep trouble because the core is probably at 400 degrees C. And so to do this, we basically used heat transfer theory. We wrote the governing equation for this problem, and we basically derived an expression for the temperature field, the transient non-uniform temperature field inside the cell, based on the thermal conductivity, the heat generation, and the diameter of the cell, based on which we derived an expression for the internal temperature and the external temperature, and the difference between the two is what we are interested in. And so, without going through the details, and we did some measurements as well. I'll skip to the final results. Some comparison with experimental data to prove the method, and finally the results are in a figure like this. So what we did here was that we took experimental data of surface temperature measurement from some old paper. Carlos Lopez and Partha Mukherjee and Judy Jeevarajan, they had, in a separate measurement, measured the surface temperature of this cell as it undergoes thermal runaway. We take that data, we use it as a boundary condition in our problem, and based on that we predict the core temperature of the cell, right? And that turns out to be this red curve, and you can see that the red curve is much higher than the surface at the peak. Question? Correct.
What if we have a battery pack? We have to determine the most critical cell.
Yeah.
Then how do we do it?
That's an entirely different problem, and I will try to talk about it a little bit in coming lectures. So everything we're talking about here is for a single cell, right? Just one single cell. What if I have a pack of 5 by 5 or 100 by 100 cells in a large battery pack, right? There, how do I go about finding which cell in this pack of hundreds of cells is the one that is undergoing thermal runaway is an open question. We'll talk about pack level thermal management in a separate lecture. Okay, so hold on to that thought. I'll certainly come back to it. You had a question?
So here also you have considered homogeneous.
Correct. Yes. The battery is assumed to be a homogeneous body, generating heat uniformly everywhere according to Arrhenius kinetics. And based on that, we solve the differential equations using the surface temperature measurement as a boundary condition. So we know that the surface temperature is a certain value that others have measured. We didn't even do these measurements ourselves. So the blue curve is taken from past work. But what we are pointing out is that, look guys, if you measured a temperature rise of a temperature of 400 degrees C on the surface and you think you're in trouble, the reality is that you're in really, really deep trouble because the true temperature inside the cell is 800 degrees Celsius. Yes? Mm-hmm.
We are just whenever we get some new electronic components, we are suggested to first charge it to its full capacity.
Yes.
And wait it till it's to 0%.
Correct.
Repeat it for few cycles.
Yes.
Then limit our charging till 80.
Yes.
And
80 and 20.
yes.
Yes.
So is this one of the preventive measures that we use?
No. The first 5 or 10 cycles of full charge and discharge is mainly to grow the SEI layer. Remember that passivation layer I was talking about? That passivation, in order to grow that passivation layer, you need to charge and discharge the cell a few times. So the first 5 to 10 cycles are related to SEI growth. The reason why we are told to keep the cell capacity between 20% and 80% is simply because at very high capacity or at very low capacity, all kinds of bad things can happen. Imagine, yesterday I was drawing an analogy between a battery and a bucket, right? If I take a bucket and if I fill it up with water, and if I keep filling it up with water, then the walls of the bucket will break, right? I'm talking about a very thin bucket here, right? If that bucket is very thin, if I fill it up all the way, the bucket might break, right? Similarly, in a battery, if I charge it too much, all the way to 100%, I'm basically putting a lot of stress on the battery material, which will cause it to fail. Usually, that failure is not catastrophic. It's not like you absolutely cannot do it, right? Once in a while, if you really need to go all the way to 100% or all the way down to 10%, it is okay. You just don't want to do it all the time. You know what I'm saying? So for example, in an electric car, if the recommendation in an electric car is also the same. Keep it between 20% and 80%. Never charge it to more than 80%. But you know what? One fine day, if I have to go a long distance and I don't want to charge in between, then it is okay for me to charge it all the way to 95%. And if I do it once or twice, it's okay, not a big problem. Okay? The thermal conductivity is also homogeneous, yes. So what we are saying is that all these materials inside the cell, there is an effective thermal conductivity. We are completely homogenizing this problem. We are neglecting the jelly roll structure of the cell and so on. And there are several other repercussions of that homogenization that we'll talk about in the coming lectures.
Thermal conductivity of this cell will vary in rate.
It does.
Radial direction and lengthwise.
Radial and axial direction, yes, the thermal conductivity is also anisotropic, and that is also something that I will highlight in the coming lectures. Here it is not considered. Here I am assuming the cell to be infinitely long, so that my thermal model is one-dimensional in space. So here is the governing equation. It's one-dimensional in R, and of course it's a function of time. So I'm assuming it to be axisymmetric and also infinitely long. Correct. Yes. So by doing that, we were able to point out through multiple papers, oops. Here was this paper by Lopez, and then you know what? I told my student, now that we have this capability, go crazy and look for such data in the literature. Look for papers that report the surface temperature of a cell as a function of time, and we can simply stick it into our model and we get plots like this. And so depending on the specific chemistry of the cell, etc., every time we certainly see that the core temperature is hotter. By how much is it hotter really depends on the cell and so on and so forth. Okay? Yes. There are. So we have another paper in which we repeat this entire process not in such extreme conditions, but under more nominal conditions, lower discharge rates and so on. And in that paper, we were able to actually drill a hole in the cell and insert a thermocouple into the core to be able to actually measure the core temperature of the cell and compare it with this theoretical technique. And the results were fairly reasonable. We were able to get reasonable agreement with the theoretical technique. Okay, if you're interested, I can point you to that specific paper as well. I do not know. I don't think any of these cells are actually undergoing charge and discharge. These are all oven tests. So what has happened here is that the cell was placed in a hot oven and then left there. And they were measuring the surface temperature of the cell as a function of time, and at some point that cell exploded and caught fire. So these are not experiments during charge and discharge. These are experiments, it's commonly called an oven test. You see, in order to understand the limits of a cell, it undergoes several abuse tests. We abuse it in many different ways. One common abuse test is a oven test. We take an oven at 150 degrees Celsius, take the cell at room temperature, stick it in and run away. Literally run away, right? Close it. The wires are coming out. We are measuring it anyway, and at some point the wires will also melt and I will stop measuring. But as far as I can, I'm going to measure that temperature. Okay. What I liked about this work, and I think you and I have talked about it a little bit, is that much of this work was able to piggyback on experimental data already available in the literature. I don't have to do everything by myself, right? If somebody else has already reported surface temperature measurements, then I can use that as an input for my theoretical model, and I can use that to predict what I expect the core temperature to be.
How you have calculated the heat generation into it?
The heat generation into it was determined using Arrhenius kinetics. So we assumed that the heat generation give me 1 second, let me get to it. We assume that the heat generation inside the cell is a strongly nonlinear function of temperature according to the Arrhenius equation, where the coefficients, the pre-exponential coefficient activation energy, come from the well-known parameters in the literature. So in the literature, there are reports of the activation energy and the pre-exponential coefficient for different battery chemistries. So if Lopez had used NMC cells, then we go to the literature and we pick out the most commonly used values of the activation energy of an NMC cell, and we use that as an input into our model. So in other words, this model does require a lot of inputs, right? And I'm not measuring each of those inputs myself. I am relying on the literature for much of that information. The other thing that goes into this model is the thermal conductivity. You can see in the governing equation that the radial thermal conductivity of the cell appears, right? In our lab, we have measured the thermal conductivity for some cells, and now that field has really exploded, no pun intended, and there are so many papers on measurement of thermal properties of cells. And so I can go and try to find out the best paper that gives me a thermal conductivity value of a chemistry that is as close as possible to my own cell. You see what I'm saying? Yeah, this was a good paper, and Mohammed Parhizi, who did that work, he went and started working for Underwriter Labs. So Underwriter Labs is a company that certifies the safety of a bunch of things, and now I think about 7 months ago he switched and he now works for Tesla. So he does very similar things for a leading electric car company. He doesn't tell me what he does because his company doesn't allow him to do that, but I suspect that he's doing something very similar for Tesla. Okay, we are coming to the end of our seminar here. You know what, I did want to talk about safety challenges at low temperatures, but I don't want to hurry it up. So I'll take about 10 minutes in the next lecture to finish this up before we start with the next lecture. Okay, why don't we take a break and we will meet again at 11:30. Okay, thank you. So let's not save this yet, Kulbhushan ji. I'll not save this yet because I'll add one more slide and then I'll save it. Okay? Yes. It's like a pressure cooker. In a pressure cooker, जब pressure बहुत ज़्यादा हो जाता है तो वो सीटी खड़ी हो जाती है, उठ जाती है, right? And the pressure is released. Exactly the same thing happens there. It's a valve which is designed to open at a certain pressure. So if the pressure inside the cell goes too high, that valve will open and it will allow the vapor to escape, which will save the cell from rupturing. Not combustion, evaporation. Yeah. At a higher temperature, the liquid inside will start evaporating, and it has only limited space inside, right? So imagine that all that vapor which is being formed is now starting to put pressure on the walls of the cell, which is why its pressure goes up. And at some point you want to relieve the pressure, which is what the pressure valve does. Yeah. You know, there have been accidents, especially with early pressure cookers. I'm talking about 40, 50 years ago, when if the CT does not work well, then the pressure keeps going up and the whole thing explodes. And it's like a bomb. It's literally like a bomb.
Nowadays also the gaskets we are using, right?
Yes.
We are working for one industry about that problem. So being a material science, they came. So how composition the polymer can be, because it has been expanded.
Right.
Expansion we are reaching them, the coefficient we are computing.
Right.
So it has to be expanded up to only certain limit.
Mhm.
We need to restrict the composition of that polyflow, some kind of compositional changes. So we have assessed with the thermogravimetric analysis what temperature it can extend, and we convert it to particular pressure. So it's
Cool.
also based on the gasket what I'm using.
Cool. Sounds good.
Flexibility how we have.
All right. So I want to take just a few minutes to finish up something from the previous lecture, and then we'll switch over to thermal modeling. Want to very briefly talk about what happens at low temperatures. So far we've talked about what happens if the cell temperature goes to 65, 70, 80 degrees Celsius. But it turns out that for many applications of lithium-ion batteries, particularly electric vehicles, we also have to worry about what happens at low temperatures, because this car that I'm designing and selling to people also needs to operate at very low temperatures. So in the US, for example, in the northern states, it's very common for the temperature in the winters to go down to minus 40 degrees Celsius. I can't even imagine what that number is, you know. I start shivering at 10 degrees Celsius. At 0 degrees Celsius, I need to go inside the house. I don't know how people survive at minus 40 degrees Celsius. And if all of us have challenges at low temperatures, similarly, batteries also have problems at low temperatures. The most important problem that happens at low temperatures is the reduced ion mobility. You see those lithium ions that have to move from the anode to the cathode through the electrolyte and separator. They move with a certain speed. And that mobility, it turns out, is a strong function of temperature. The mobility of ions goes down as temperature goes down. Right? We all are very active at this temperature. If it was 10 degrees Celsius or 5 degrees Celsius, we'll just sit down in one place and not want to go anywhere. Right? Ions also do something similar. And because the mobility of ions goes down, that leads to both capacity fade and, more importantly, power fade. Power fade is a more critical phenomena here, because in order to get current out of my cells, I need the ions to move. Right? The more ions that can move, the more current I can get out of the cell. But if my ions are not willing to move, if my ions are sluggish, then I will not be able to get a lot of current out of my cell. So that's the key challenge that occurs at low temperatures. To the best of my knowledge, there is not a catastrophic failure that will occur at low temperatures, similar to thermal runaway. Right? So this is not an emergency scenario. This is just a problem. My car will run slow, or my car will not go as far as it used to go, but it won't explode or it won't catch fire or something like that. Nevertheless, this is a strong enough problem that there are all kinds of things that are done to prevent the reduction in ion mobility. Most commonly what happens is that if I have a pack of cells, then inside this pack you will have designed a heater to provide some heating to the cell pack in order to raise its temperature. So in a car like Tesla, for example, the car will sense the external temperature. If the temperature is too low, then it will use its battery to provide current to heat up the battery itself, right? It's sort of like eating a part of me to be able to survive, very crudely speaking, right? The charge inside this battery is used, it is run through a resistor in order to heat up the car itself. I've not experienced this myself, but I'm told by my colleagues who live in cold climates that when you start the car early in the morning, it does run slow. The acceleration is not that fast and so on. And the car makes a lot of noise because there's a lot of current passing through these resistors in order to heat up the cold battery pack. Once the battery pack reaches a certain uh, a certain temperature, then at that point the car is back to normal. Okay, so that's the main effect at low temperatures, because of which in applications like electric vehicles you have to provision the capability of heating up the battery pack. In this context, there is a very nice piece of work by uh, by a group from Penn State, C.Y. Yang, C.Y. Yang, C.Y. Wang, I think. I'm not 100% sure. C.Y. Wang, okay, good, good. So what they have done is, they have said, okay, here is my cell. It has an anode and a cathode, and I'm drawing it schematically here because this is not exactly how it looks. In addition to that, they place a nickel foil, just a plain foil of nickel, and they are able to pass current through this nickel foil if needed. And this nickel foil heats up and it provides heating inside the cell itself. So instead of heating up the entire big thing, the entire battery pack, you are heating up exactly what you need to heat up. Do you see what I'm saying? And they have a bunch of papers, a series of papers that show the benefits of a construction like this. Conceptually, it is very similar. It basically draws current out of the battery itself and uses it to heat up the nickel foil, and it leads to very beautiful results of how fast you can heat up the cell. In this approach, it takes several minutes to heat up the cells. Here, it takes a few seconds to heat it up. Okay? Probably in the context of India, this is not important because the temperatures in India just really don't go down as much. So most electric scooters or electric cars designed for the Indian climate probably don't have to worry about this. Even if you go to Kashmir in the peak of the winters, I don't think the temperature is so low that you have to worry about stuff like this. Okay? Any? Below minus 20 degrees or so, right? It continues to happen, but it really accelerates below about minus 20 degrees Celsius. Below that, it becomes a real troubling problem, and you have to do something about it.
There was an issue with the electric Tesla car in the snow during the snowfall.
Yes.
The bunch of cars are just stick on. They are not able to run also.
Correct.
Because of this cold started.
Yes, so essentially the same problem. The cars are so cold that it becomes very difficult to accelerate those cars, and more importantly, the process of charging the car is also a function of temperature. So imagine I have, again going back to the concept of a bucket. If I want to fill up this bucket or the battery, the temperature of the battery plays a very important role. It turns out that the speed at which you can charge a car goes very low at lower temperatures. The colder the battery is, the slower will it charge. And so if I was able to charge my battery, my car in a few hours, it will take 10-15 hours to charge that car at low temperatures. In fact, to solve that problem, Tesla has an internal heater inside the battery pack. So this internal heater in the battery pack is used not only for cold start, but it also used for charging. So if I tell my car that, look, I'm driving to a supercharger where I'm going to charge the pack very, very fast, then the car will start heating up the battery pack in advance. It's called preconditioning. So that when I charge my car, the battery pack is already warm. By the way, that is a very delicate game. You don't want to heat it up so much that it causes problems, right? You want to heat it up just a little bit so that it is nice and warm and you're able to pour a bunch of charge into it very fast.
Another follow-up question is, what will be the desirable temperature condition, environmental condition to function a battery at its max?
So if you open the spec sheet of any battery, any lithium-ion battery, the manufacturer will give a recommendation for the minimum temperature and the maximum temperature. Typically those numbers are 20 degrees C low and about 60 degrees C high. Probably a safety factor there. So my guess is maybe 15 or 10 degrees C to 70 degrees C. You don't want to go above or below that limit. Okay. By the way, talking about charging, we all are conditioned to be able to fill up a car or a scooter within, how long does it take? A regular car or a scooter. You go to the gas station, petrol pump, max to max 2-3 minutes, right? If there's no queue, exactly. If there is no queue, that's a very good qualifier. If there is no queue, it takes about 5 minutes for the actual act of filling up the car. Electric vehicles are competing with that perception. You see, I want to be able to go to an electric vehicle charging station and be able to charge my car in 5 minutes flat. It turns out that that is an extremely challenging problem. If you give me 4 hours to charge it overnight, wonderful, great, it will happen easily. But if you want to charge the car very, very quickly, then that is what takes a lot of challenge. And that is why people are coming up with all kinds of techniques. For example, mild heating. It has been shown that if you heat up the cell mildly, it is the same effect related to ion mobility. A slightly warm cell, the ions are going to move faster. And as you pump a bunch of electrons into it, the electrons will move around faster and find their home. Whereas if it is cold, then it will take longer for it. That is the reason for the internal heating, even for charge and discharge. Does that make sense? Any other questions before we shift our gears? Yes?
One more. We know that SEI formation is happening when we go for initial
Correct.
charging discharging for 10 or 20.
Correct.
But what happens when we increase the cycle, as the cycle of charging, the number of cycles increases for a single cell of battery pack?
Yes.
This SEI also start growing?
Yes, the SEI is also growing. However, I had a picture of the SEI here, right? The first layer, you see, when I have virgin aluminum, the first layer of aluminum oxide grows very fast because the oxygen can contact the aluminum right away. But after a certain thickness of aluminum oxide has grown, then this oxygen has to diffuse through the aluminum oxide to access the fresh aluminum. This process of diffusion is a slow process. And as this aluminum oxide grows, it takes the oxygen longer and longer to travel to the aluminum. To the extent that at some thickness, there is barely any oxygen that will be able to go all the way and grow the SEI layer. So in principle, the SEI layer continues to grow throughout, but its rate of growth becomes so slow that practically speaking, it's only the first 10 or 20 cycles during which the SEI grows. After that, the growth does not stop to zero, but it is extremely small.
So what are the mechanisms when we increase the number of cycles for a battery and its nominal capacity start to fading up as the number of cycles grow?
Yes.
So is it that SEI growth is the one of the reasons?
No, SEI growth is not the main reason for the reduction in capacity. In addition to SEI growth, there are also other irreversible side reactions that are happening, such as lithium plating. So there are chemical reactions happening on the electrodes themselves in which lithium is consumed irreversibly. So instead of the lithium intercalating into the electrodes, there are other places where the lithium goes and is captured and is not released again, which is the reason why the amount of lithium available, the amount of active material available inside the cell goes down as a function of time, and that is why its capacity goes down.
And generally, SCI formation happens at the interface of separator and electrode, or electrode and electrolyte.
At the interface between the electrode and the electrolyte. Only on the cathode side, I think. Is it cathode or anode? One of those two. Yeah. Doesn't happen on both electrodes, only on one of them. Yeah. Any other questions here? Alright. Give me a minute to save this and then I will start a new sheet. Alright, we are good to go. So let me close this. No, I don't. I already saved it, so I'm okay to go. So this is lecture number 5. What I want to do now is to start talking about thermal modeling of lithium ion cells. The basic idea that if I have a cell that is undergoing charge and discharge, I want to be able to predict its temperature rise. I want to know how hot it gets and where does it get the hottest, what is the temperature field around it, for which what I would like to do is to write the governing equations for the temperature field and then solve those differential equations. So just take a couple of simple examples. Here is a prismatic cell versus a cylindrical cell. There is heat generation happening inside these cells, because of which these cells will get hot, right? And I need to understand how hot these cells will get, right? So the question is, what is the temperature as a function of x, y, z and time, or in this case, what is the temperature as a function of r theta z and time? And to answer that question, we have to write the differential equations that govern the temperature field and solve those differential equations. Okay? In this class, I am not going to derive those differential equations from scratch. Let me simply write the governing energy conservation equation in its full glory. So for the Cartesian system, the most general equation looks like this: kx del t del x plus del by del y of ky del t del y plus del by del z of kz del t del z, all of this plus q triple prime equals rho cp del t del t. In general, this is a considerably complicated differential equation. It's second order in x, y and z, first order in time, it is non-homogeneous, it is non-linear, and so, you know, this is perhaps not as complicated as the Navier-Stokes equation, but nevertheless it is fairly complicated. In the radial coordinate system, I can write 1 over r del by del r of r del t, there's a kr here, plus 1 over r square del by del theta of k theta del t del theta plus del by del z of kz del t del z plus q triple prime equals rho cp del t over del t. I can spend an entire course deriving these equations and talking about how these equations are solved, but instead in this course I am going to look at these equations in the specific context of lithium-ion batteries alone. Okay, some good books to go read more about this are the book by Ozisik, Heat Conduction, I think is the name of the book. And another good book to read is by Myers. Glenn Myers. OSISIC is a very good mathematical book where you can get all the details of the math. Myers is somewhat easier to understand, and I would recommend starting from Myers and then going to OSISIC. Oh, and by the way, if you're happy enough with OSISIC, I mean, if you're excited by OSISIC and you want more, then the Bible of this field is Carr's Law and Jaeger. Carr's Law and Jaeger is a very compact but very dense book. It takes time to read it. You have to read it 2 times to be able to understand what they are saying. But almost anything and everything that we do is already available in Carr's Law and Jaeger. Okay, so this is sort of increasing level of difficulty and comprehension. Correct, yes. So here the thermal conductivities, I'm using the subscript X, Y and Z, which means that my thermal conductivities are different in the 3 directions, right? So I'm assuming the thermal conductivity to be anisotropic. So K here is anisotropic. I think yesterday I gave you an example of a copper block which has the same thermal conductivity in all 3 directions, but in comparison, if you look at a carbon composite containing carbon fibers, then the thermal conductivity can be different in the 3 directions. Tomorrow in our lecture I will show how thermal conductivity of lithium ion cells also is highly anisotropic. In fact, in our lab that was the very first paper we wrote in which we measured the anisotropic thermal conductivity of lithium ion cells. I'll show that paper tomorrow and discuss it very briefly. I think that for us was the paper that started it all, right? It was from there that a bunch of ideas flowed, and even now if you look at my Google Scholar, that paper is the most cited of all of my papers. Makes me very happy about it. Do you guys mind if I go into some side stories, or should we stick to stuff? Huh?
That will be a engaging aspect of every teaching.
Okay, good.
Not only you, but we are doing.
Good. All right. So the story about this is that this guy called Stephen Drake shows up in my office and says, Dr. Jain, I want to work with you. He had no idea what he wanted to work on. I was myself a young assistant professor at that time, and I had no idea what I wanted to work on. Okay. One day he and I were sitting in my office, and this other faculty from electrical engineering walking past, he comes into my office and says, look, I am working on some project with the Navy. Our cells are getting very hot. Can you do something about it? And I said, okay, let me think about it. And I sort of waved him off. But 2 days later, I was doing a Google search, and that paper by Todd Bendhauer showed up. And I read that paper in detail, and that is when I realized the importance of this field, right? More importantly, not many people from the heat transfer community were working on batteries at that time. And so in some sense, I just happened to be in the right place at the right time, right? It's important as you grow to be able to identify what are the good problems to work on. You don't want to work on a problem where there are already 1,000 papers written in the last 15 years, right? You want to try and come up with something new, something different. Because in a new field, in a different field, where there's not a lot of work already done, even minor work that you do ultimately ends up getting cited very much and becoming very important, because you can then claim that you were the first one to do something. So for example, in the paper I'll show tomorrow, Stephen Drake and I then followed up the discussion with this other professor, did some very simple measurements. Those measurements are actually fairly straightforward, but we were able to prove experimentally that the thermal conductivity of the cell in the radial direction and in the axial direction are very different from each other. And we'll talk about the reasons why tomorrow. But that very simple insight, we were able to publish in a good journal. And now it has like 300 plus citations. Okay? So I want you all to be open to new ideas. Don't close yourself too much. Yes? Correct. Yes. Correct. So the thermal conductivity and heat generation rate are completely independent of each other. It is possible that the heat generation may be occurring uniformly, but the thermal conductivity may be anisotropic. You see what I'm saying? Just because we assume the heat to be generated uniformly does not mean that we must also assume the thermal conductivity to be uniform or isotropic. I could have any combination of the two, right? Uniform heat generation, isotropic thermal conductivity. Uniform heat generation, anisotropic thermal conductivity, and all the four possibilities. You know what I'm saying? The two are completely independent of each other. I will talk about when it may be possible for us to assume the thermal conductivity to be a constant number. Okay, we'll talk about that very briefly. In fact, I think we are ready to talk about it right away. So let's just take a simple example. If I have a cylindrical cell, if this cell is long enough, then I can assume that thermal conduction in the z direction is negligible, right? If this is an infinitely long cylinder, then I can neglect heat transfer in the z direction, and I can assume heat transfer to occur only in the r and theta directions. This is the radial direction, this is the theta coordinate. So very long cell can be assumed to be no dependence on z, correct? Further, if the cell is symmetric, not only the cell but also the external conditions, meaning that as I go around theta, if everything is the same, not only inside the cell but also outside the cell, then I can neglect theta dependence as well. You see, as engineers, one thing that we do very well is to simplify our problems as much as we can so that we can solve those problems. Right? Scientists will probably not like this. They want to solve the whole problem even if it is very difficult. But us engineers, we want to solve a problem even if it is an approximate solution. Right? So in the spirit of approximation, these assumptions are made very commonly. If I make these assumptions going back to the previous sheet, I can neglect this term, I can neglect this term, and my equation starts becoming fairly simple. Let me write that simplified equation here. It is 1 by r del r of k r del t del r plus q triple prime equals rho cp del t del t. Where you will notice that I have dropped the subscript on k, which is mainly because if there is only one direction, then k means thermal conductivity in the radial direction, right? What is the type of this equation? It's a differential equation. What kind of differential equation is this? It's a partial versus ordinary. It's a partial differential equation. Partial differential equations are much more difficult to solve compared to ordinary differential equations, right? Not just slightly more difficult, much more difficult to solve compared to ordinary differential equations. Therefore, it will be our effort whenever possible to approximate and convert this partial differential equation into an ordinary differential equation. So for example, if we consider steady state, if the cell has been running for a long time, then eventually it will reach an equilibrium, and I want to know how hot it is at equilibrium, right? That stage is called steady state, and steady state basically means that nothing changes as a function of time, which means that this term del T over del T can be ignored, and I can write 1 over r del T del r of k r del T del r plus q triple prime equals 0. It is this equation that I need to solve in order to find out the temperature profile in the body. I am demonstrating this for a cylindrical cell But everything that we are doing here also equally applies to a prismatic cell. Okay? So this is the equation that I want to solve, and a mathematician will look at this and say, what crap, you should not be using del sign, you should be using the d sign. Yeah, but I'm taking liberties with mathematics a little bit. Why not? In order to solve this equation, I need what? Boundary conditions. I don't need initial conditions because it's a steady state problem. Tomorrow we will look at transient problems as well. For now, let's focus on steady state problems. How many boundary conditions do I need? No, 2. The answer to that comes from the order of the differential equation. This is a second order equation, so it needs 2 boundary conditions. In this case, the boundary conditions will come from r equals r and from r equals 0. We discussed this very briefly in the tutorial yesterday. The r equals 0 boundary condition is a little weird. Usually we say that the derivative of temperature at 0 must be 0. Or we simply say that T must be finite. This is the finiteness requirement at r equals 0. At r equals r, I can think of a more comprehensive boundary condition. What is happening on the outer surface of the cell? I must describe it mathematically and write it as part of this boundary condition. Okay, so most commonly outside the cell I have some kind of a flow which is removing heat from the cell, right? So this cell is sitting here, I'm blowing air over it. Even if I'm not blowing air over it, there is some natural convection happening in the vicinity of the cell, because of which there is some convective heat transfer. Remember in the very first or the second lecture yesterday, we talked about 2 modes of heat transfer, conduction and convection. This is convective heat transfer, and mathematically convective heat transfer is characterized by the convective heat transfer coefficient H. In fact, if you recall from the lecture yesterday, the convective heat loss at the surface is given by H times T minus T infinity. Correct? So at the outer surface, what we can write is that this convective heat transfer must be equal to the conduction heat transfer reaching the surface, right? Whatever is leaving the surface must equal whatever is reaching the surface for equilibrium, right? The surface cannot store or destroy energy or generate energy, and therefore here I can say that Ht minus T infinity must be equal to negative K del T del R. This is Fourier's law. This is the conduction heat transfer. This is Q double prime conduction. In other words, if I am sitting on the surface, whatever comes in must equal whatever leaves. This is what is coming in, this is what is leaving, the two must be equal to each other. It is in, yes, exactly. Even if it is not in equilibrium, even in transient, the surface is so thin that it cannot store energy. Therefore, sorry? Correct, yes. And therefore, whatever comes in must instantaneously leave. Just applying energy balance at the interface, at the outer surface of the body. So I want to solve this equation subject to these 2 boundary conditions. Yesterday for the tutorial I had used a simpler boundary condition here, but today in more detail I want to go into the details of how this equation will be solved. Okay? So you all are good at math, we can solve this equation very, very, very fast. We'll have R we'll have K Let me just write it again. Sorry, I'm not as good as you all are in remembering these things anymore. Yes, so now let's solve this. I have R K del T del R equals negative Q triple prime R squared by 2 plus C1. This is actually very similar to our derivation yesterday, and this becomes C1 over R, correct? And then if I integrate it once more, I get T equals negative Q triple prime R squared by 4K plus C1 over R plus C2. To be mathematically correct, let me move this K to the other side right away. Okay? Then similar to the tutorial yesterday, this term goes to 0. Sure, it doesn't matter. This should be log R. 1 second. Plus C1 over R, it's fine, right? Is this okay so far? Yes or no? Okay, then the next step would be T equals negative Q triple prime R squared by 4K plus C1 log R plus C2. Is that okay? Good, thank you. Thank you. Here, C1 can be set to 0 due to the boundary condition at R equals 0. And therefore the rest of it is there. I still need to find out the value of C2, for which I will use my boundary condition here. So it is negative K dt dr, which is minus Q triple prime R over 2K, correct? Must be equal to H times T minus T infinity. From where I can find out the value of C2. So C2 is equal to T infinity plus Q triple prime R over 2H. I want to take the H to the other side, plus Q triple prime R square by 4K. Did I get that right? How do we know that this is right? Or how do we know that this is not wrong? By the way, those are two very different questions. Yeah, how do I know that this is not wrong? I can insert the units to see if it makes dimensional sense. So Q triple prime is watt per meter cube, R is meter, and H is watt per meter square Kelvin. And this is units of Kelvin, which it should. Let's check the second term. Sorry, the last term. Watt per meter cube, meter square, and K has units of watt per meter Kelvin. So that also makes sense, right? What this shows me is that what I have written here is probably correct. I don't know that it is exactly correct, but it is at least not grossly incorrect, right? All right. I think this is fine. I think this is fine. So from there, what we can write is T as a function of R is equal to T infinity plus Q triple prime R over 2H plus Q triple prime R squared by 4K minus going back to the previous slide, no, right here, minus q triple prime r squared by 2k, no 4k. Actually, these two terms can be combined. That's my final result. This is a very straightforward calculation, but nevertheless it tells us a lot of things. It tells me what the temperature field in the cell is going to be, particularly the maximum temperature will be the temperature at R equals 0, which would be T infinity plus q triple prime R over 2h plus q triple prime R squared by 4k. Okay? This is the highest temperature that will happen inside the cell. Clearly, it's a function of q triple prime. It's a function of the radius of the cell. It's a function of its thermal conductivity as well as the convective heat transfer coefficient. So what this says is that if my heat generation rate goes up, so does the temperature in a linear fashion. But remember that q triple prime itself was proportional to I square, which means that as the current inside the cell goes up, the heat generation will go up dramatically. If the current goes up by 2 times, the heat generation will go up by 4 times. And God forbid, if the current goes up by 10 times, then the heat generation will go up by 100 times and you will be in a lot of trouble. Right? If at a certain current, the maximum temperature rise is only 1 degree Celsius, you're okay. But if the current goes up by 10 times, that same maximum temperature or temperature rise will go up by 100 degrees Celsius and you will be in a lot of trouble then. So you see guys, we, especially in the PhD process, get into the details of a lot of things, right? We go down into every tiny little minute details, but oftentimes it is these back of the envelope calculations that are really important to give us an insight into the problem. This problem tells me, if somebody comes to me and says, I want to run this cell at a higher current, how hot do you think it will get? This analysis tells you roughly how hot it will get. And oftentimes, really, that is all that you really need to know. You don't need to run a finite element simulation and run a calculation, write a code, take 2 weeks to get back to him or her, right? That person needs an answer right now so that they can decide the direction in which their manufacturing process will go and their design will go and so on. You can tell them that, look, you increase the current 10 times, it will be disastrous. Simple answer. You increase the current 2 times, maybe you will still be okay. Right? A good engineer needs to be able to do both things. You need to be able to find a back of the envelope answer in 5 minutes, and you need to be able to find an extremely detailed answer in a period of 2 weeks, if there is that much time. The PhD process makes you very good on the second part, perhaps not very good in the first part. Hopefully you will learn the first part if you go and work in the industry after you're done with school. Because there people really need to know the answer very, very quickly, even if it is not the exact answer. Okay? This analysis also tells us that the higher the value of H or the higher the value of K, the lower will the temperature be. So you can make a provision to increase the cooling on the outer surface of the cell, based on which H will go up and your temperature rise will come down. So the more air you blow over it, the higher will be the value of H, and therefore the lower will be the temperature of the cell. However, it turns out, if you recall from the previous lecture, that H depends on the velocity, the fluid properties, the geometry, etc. Remember yesterday we said that a smooth plate versus a rough plate, the value of H will be different. A cylindrical a cylindrical tube versus maybe some other random shape, the value of H will be different. Unfortunately, in this problem, the shape of the cell is probably fixed. You cannot possibly go to them and say, just in order to get a 10% improvement in thermal conductivity or in heat removal rate, I want you to change your entire manufacturing line and start building star-shaped cells rather than cylindrical cells, right? So, to a great extent, changing the geometry or changing the geometry of the cell is out of question. You cannot say, provide some roughness on the cell surface. Nobody is going to ever listen to you, right? The properties of the coolant, this is the properties of the coolant, not the cell itself. The properties of the coolant are also more or less fixed. You're going to use air or water. Those are the two most common coolants available out there, right? There's not much you can do about the thermal conductivity or the viscosity or whatever of air or water. That is also sort of fixed. The only thing that you can practically change is the velocity at which you blow your coolant over your cell. And unfortunately, if you were to plot the Nusselt number, which is the non-dimensional representation of H, versus the Reynolds number, which is the non-dimensional representation of velocity, then this curve sort of plateaus out. You cannot keep making the flow faster and faster and faster to increase the value of H on and on and on. It sort of does not change anymore. So there are upper limits to how high H can go. Moreover, if you look at our result here, you see H appears in the denominator only for one of the terms, not all of them, which means that even if H was extremely high, this term would become 0, but the other term would still survive, which means that you make H infinity if you can, even then there will still be some temperature rise, correct? In fact, the reason for that is that in this process of heat removal, the heat generated inside the cell has to pass through two resistances. One is the resistance inside the cell, and the other is the resistance at the interface. So this is R internal, and this is R external. By increasing the value of H, what we are doing is that we are making this external resistance close to 0. But even if you make that close to 0, the internal resistance will still be there, and it will still cause an increase in the temperature of the cell. So not only do you need H to be very large, simultaneously you want the thermal conductivity also to be very large.
We increase the velocity, right? The air is continuously, fresh air is continuously in contact with the battery, then it will work as an insulator.
No, it won't work as an insulator. It'll
Conductivity of the air will be too low, and we have increased the air flow so much high.
If you increase the velocity of the air to very high values, what will happen is that the temperature of the air, T infinity, will, the surface of the cell will become at T infinity. But that is the best possible thing that can happen. The temperature of the surface cannot go below T infinity, right? I can't bring the cell temperature to below the temperature of the coolant itself, right? Increasing the value of H to infinity essentially causes an isothermal boundary condition. The convective boundary condition becomes an isothermal boundary condition in the limit that H goes to infinity. You can actually see that mathematically here. If you take H to the other side, for example, and if H becomes infinite, then this term will become 0, and I'll have T equals T infinity, right? So the isothermal boundary condition is a special case of this convective boundary condition in the limit that H goes to infinity. That is the best possible cooling that you can get, in which case the surface of the cell is at T infinity. But even then, there is still some temperature rise in the cell because of this other term that will survive even if H is infinitely large. And if you want to reduce that term as well, you must increase the thermal conductivity of the cell. Okay? In one lecture tomorrow, we will go into a lot of details of the thermal conductivity of the cell itself, right? But I'll give you sort of a sneak preview of what we will see there. You see, inside the cell today, earlier today, we saw that the cell is made up of the anode, separator, cathode, and the current collectors. All those sheets that are put together and rolled and placed inside the cell. It turns out, we will learn tomorrow, that each of these materials has a reasonably high thermal conductivity. But when you put them together, the thermal conductivity of the cell itself is actually quite poor. Thermal conductivity of typical lithium-ion cells, K is typically around 0.1 to 1.0 watt per meter Kelvin. Those are fairly poor numbers. If you may recall, the thermal conductivity of copper is 400 watt per meter Kelvin. This is more like the thermal conductivity of typical plastic materials, a very low value. Even water has a higher thermal conductivity than this. And in fact, the paper that with Stephen Drake that we wrote, we exactly talked about this. We said that, look, we are seeing very poor values of radial thermal conductivity of the cell, which is why we predicted in that paper that there's going to be lots of problems related to heat transfer in this cell. Since then, there's probably 100 papers that have been published on measuring thermal properties of cells. There is in fact a very good paper by Greg Offer, O-F-F-E-R, that summarizes that entire field of thermal properties of lithium-ion cells. And he has like 200 references to other papers that measure various thermal properties of all kinds of cells. Question? Do you have a question? Okay. Any questions? Yes. Do you mean this resistance that I drew here? Yes. Keep in mind that these two resistances are not electrical resistances. These are thermal resistances. Okay? You see, just like we have Ohm's law for electric current, what is Ohm's law? If this is V1, V2, and if this is the resistance, then Ohm's law is I equals delta V over R. Correct? Similarly, if I have a body in which one side is at a temperature T1, the other side is at a temperature T2, then the amount of heat that flows, Q double prime, is equal to delta T over R thermal. In other words, I can describe this problem using a resistance network using essentially like a resistance. So for a lot of problems, heat transfer can be described in the form of resistances. Strictly speaking, I should call them thermal resistances because they are not electrical resistances. So that resistance that I drew here, sorry, I didn't specify that, is not a electrical resistance. It's not related to the mobility of ions inside the cell. It is related to the thermal conductivity of the cell. Okay? The internal resistance, let me just write it here, R internal is because of how heat flows inside the cell, and it is connected to the thermal conductivity of the cell. The higher the thermal conductivity, the lower is the internal resistance of the cell. and the other one, R external, is connected to the convective heat transfer coefficient on the outer surface of the cell. The higher the value of H, the lower would the external resistance be. Another way to think about this is that if I am a packet of heat that was generated at the core of the cell, I must first travel through the cell to reach the surface.
So that means that is due to the difference of the temperature inside and outside.
Correct. Yes, that is what governs the temperature difference between the inside and the outside of the cell. One more way to think of this is that if I want to fly to the United States, the first thing that I need to do is to get to the Delhi airport and then take a flight from there, right? How fast I can reach the United States depends on how fast I can get to the Delhi airport, as well as how fast can I catch a flight from there. If there are flights leaving the Delhi airport every hour, but there's a bus leaving from here only once a day, then which step determines how fast can I get to the United States? It's the bus, right? Because the frequency of that bus is much lower. On the other hand, if there were buses leaving every hour, but only one flight a day, then the rate determining step would become the flights. Because these two resistances, the resistance of the bus that I need to overcome and the resistance of the flight that I need to overcome, are connected in series with each other. When I have two resistances in series, the larger resistance is the one that determines the dynamics of the problem. Similarly here, even if I was to increase the value of H to infinity, that's roughly like one flight leaving every hour or every minute in an extreme case. Even then, I cannot get to the surface quickly enough because there's only one bus leaving every day. That is what happens when the convective heat transfer coefficient is very large. I'm doing everything I can on the outside, but inside there's not much that I have done. So in some papers I will show tomorrow, we make a case for increasing this value as much as possible. We showed that by increasing this value by 3 times, I can reduce the temperature rise roughly by that extent. But how do I change the thermal conductivity inside the cell is the next question, right? And we will address that in a lecture tomorrow or so, right? Given having identified that thermal conductivity plays an important role in determining how hot the cell will get, now the question is, what can I do about the thermal conductivity of the cell? That will be the topic of a very interesting lecture either tomorrow or the day after, I forget. It's there on our agenda. When we get to that, we'll discuss a couple of papers that were written by my students. That paper has an IIT Ropar connection. Vivek Vishwakarma, who was an undergrad student here at IIT Ropar long time ago in the transit campus, came to me to do his PhD, and the paper I will discuss is indeed the work that he had done. So I'm really looking forward to that. Yeah? All right. Any other questions or comments? देखिए, thermal conductivity change करने के लिए material change करना पड़ेगा, right? Different materials have different thermal conductivities. नहीं, thermal conductivity is usually a weak function of temperature. It does change with temperature, but not very strongly. अगर हम चाहें कि वो thermal conductivity strongly change हो, 0.1 से 10 watt per meter Kelvin हो जाए, suppose, right? तो I can make a big difference. But वो करने के लिए हमें material ही change करना पड़ेगा. Copper has a thermal conductivity of 400. If I can fill my cell with copper, all my thermal problems will be solved. But it won't be a battery anymore. Right. Right. No, these materials typically don't undergo a dramatic change in their structure. There are papers out there that have measured the thermal conductivity of a lithium ion cell at different temperatures, at 30 degrees C, at 45 degrees C, at 60 degrees C. Maybe something dramatic will happen at 300 degrees C, but I don't care, because the cell is only going to operate between 30 degrees C and about 60-70 degrees C. If it has a fantastic thermal conductivity at 400 degrees C, good for you, but it has no benefit for me because the cell will have exploded by then anyway. Yes. होगा, लेकिन अगर if it is outside the temperature range of interest to me, तो फिर I'm not going to study it in the context of lithium ion cells. Maybe for other applications, solar cells or whatever, what you're saying may be relevant, but here it does not make any difference to my analysis.
We want the structural stability in our electrodes.
Correct. Yeah, so
If thermal conductivity increase by temperature, but the structure will
exactly.
if the structure will change, then
Yes.
it will create more problems.
Yes, it's a multi-physics problem, right? I want to remove heat, but more fundamentally, I want to store energy, right? I can fill it up with copper, as I said, and it will be a great conductor of heat, but it won't be a battery anymore. So I have to walk very carefully here. Whatever structural changes that might happen with temperature, which might increase its thermal conductivity, should not reduce the charge storage capacity of the cell. If it does, then the improvement in thermal transport is of no use to me. Does that make sense? Any other questions? If not, why don't we stop here and we will meet as scheduled at 2 o'clock. I think we are almost right on schedule. We'll start the next lecture at 2 o'clock sharp. It will be given by Dr. Agrawal, who will be here at 2 o'clock, and we'll start right on time. Okay. Do you have any logistic announcements to make? Okay. All right, then I'll see you all at 2 o'clock. Thank you. Okay.
Let me know. Fine. So let's start today's discussion. So in yesterday's session, we actually went to in great detail about what are the governing equations and how you can actually model the everything inside the battery system, right? So before we go and actually is going to come, I'm just waiting for one of the student because he asked me something of after the class. Anyway, I can start with that and in the meanwhile, fine. So okay, so just a very quick recap of what the things that we did yesterday. That I told you that this is the overall model of the battery system in its full glory. That means there are particles which are also known as active particles. There is electrolyte which is present everywhere, right? And there is a separator in between, right? All these things we saw that what are the, there is a current collector, right? And then I told you that there are various ways or various level of detail by which actually you can model the battery, right? We in yesterday class we went through the micro scale modeling. Today the goal is going to be uh, covering the aspect of the homogenized model and the DFN model. These two we want to cover it today, okay? And that is the goal, and this was the overall schematic. So we will continue to use the similar symbols and notation that we have used yesterday, and this was kind of, if you put it, this is what actually we did yesterday. So these are the all the equation. Before we actually jump into this thing, I just wanted to clarify one thing. And okay, fine. Okay, so let's think about the thermal system, right? So in thermal system, the governing equation is del Q by, sorry, del T by rho Cp plus del dot Q equal to 0, where the Q is minus K del T. This is the overall equation, right? Fine. Now, if I take a particular domain where I want to solve the heat transfer problem, this thermal equation, then apart from this governing equation, what I need is, I need the boundary condition, right? So that means either on the part of the boundary I will be prescribing the temperature, which is known as Dirichlet boundary condition, or I will be prescribing the Q, the heat flux, which is known as Newman boundary condition. Okay, and the thing that I wanted to highlight is, let's say for whatever reason there is a bit of heterogeneity in the domain. Okay, so it is of the material 1 and this is the material 2, right? So apart from the boundary, now there is a new thing in the problem, okay, and that is the interface between the two domains, right? So apart from the boundary condition, we need what are known as interface condition. What is happening at the interface, right? So in case of thermal problem, the at the interface, the condition is the temperature that is there at the M1 domain in the boundary is going to be equal to the temperature in the M2 domain. Okay, so that means that there is a continuity of the temperature field. Okay, apart from that, this is not in actually apart from this, there is a continuity of heat flux. Okay, so the continuity of the heat flux is that the Q dot N in the material domain 1 is going to be Q dot N in the material domain 2. Fine. Okay, so this is, so at the interface also you require some condition, right? Now apart from this condition that is there, let's say now let me make the problem slightly more complicated. Okay, now let's say there is some kind of heat source. There is a, let's say, wire that is, I inserted some kind of wire, I am flowing the current. So now there is going to be some kind of localized heating at the interface, which is going to be given by some formula like something like I square R. It doesn't matter. Ultimately, there is some kind of heat source, right? Then this continuity of the heat flux will no longer be there. Okay, then it will be like Q dot N M1 minus Q dot N M2 will be equal to the some kind of heat source that you have generated per unit area. Okay, so interface, so all I am trying to connect here is apart, so for, or you also require initial condition, because if my plate is already was there at 100 degrees Celsius, the final response is going to be different. If my plate is 50 degrees Celsius, the final response is going to be different, right? So I need the initial condition, that is T at T0 at T equal to 0, even that is required, right? So right, so in any arbitrary problem these things are required: one, initial condition, boundary condition, and third, interface condition. Okay, so now let's come to the equation and let's revise what we have done. So this is, I told you that there are two domains. One is the electrode domain, another is the electrolyte domain. In the electrode, we saw that the first equation is the conservation of the lithium in the electrode particles. The second equation is a conservation of the charge again in the electrode particle, that is happening because of the flow of the electron. This one is the flux, that is given by the diffusion constant and concentration gradient. So this is how the flux and the concentration is rated. The last one here is Ik equal to sigma k del phi k, where the sigma k here is the conductivity, normal electronic conductivity. Okay, fine. So these are the four things that we have in the electrode. Now in the case of electrolyte, we have the conservation of the lithium ion. The second one is conservation of the charge again. Now this flux is related with minus dc del c. There is the additional term, and this additional term is coming because I told you that in case of electrolyte there is a movement of the ions because of the electrostatic field, sorry, because of the electric field also. So that's why we have this IE, right? And T plus is the how much the positive ions are contributing to the current. Now this was the final equation where we have the current which is dependent on the electrostatic potential and the concentration, right? The one thing that you have to pay attention, this sigma is not the usual conductivity of the electronic conductivity. because in case of electrolyte the flow is happening due to the ion, so this sigma is actually the ionic conductivity, not the normal conductivity that we know. Okay, fine. Now this is fine, right? Now if I go back to the previous domain, now this was the governing equation. Now we have to take care at the interface, right? There is an interface between the electrode particle and the electrolyte, right? So if I'm not sure, I think I should use this one. So otherwise the notes will not be created. New, right? It is saved, right, or no?
This is safe, so you can close it from the top right.
Top right.
Just close the whole window.
Okay, okay.
You can save it. No, sir. In the center. In the center.
Okay.
Save it.
Yeah. No.
Or, yeah, no is better.
Okay.
Now,
This is-
the green thing and the, yes, that opens a new file.
Fine. I think that's it. So this is a particle here, and so this is the electrode, active particle. And there is a electrolyte. Sorry, it's not. I think it will take some time. Right. So there is a interface now between the two domains, right? And in the interface there is a reaction that is happening, and that reaction is lithium is decomposing in the lithium plus electron. Okay, and this is the fundamental equation that is happening. The one thing to note here is this is actually not a one-way equation. At either at the positive electrode or negative electrode, the reaction is happening in both directions simultaneously. Always, whether the charging of the battery is taking place or whether the discharging of the battery is taking place, the reaction is happening in the both direction. It is never happening in a single direction. Based on the condition, sometime, so this forward condition is known as reduction, oxidation. So this is forward is known as oxidation and the reversal is known as reduction, right? So this the only thing is which is dominating. Sometime oxidation will dominate, sometime the reduction will dominate based on the position and based on the charging or discharging. But both are happening at the same time, right? So the current that is overall flowing is given by J equal to J naught, right? And then we have e to the power 1 minus beta f eta r t minus e to the power minus beta f eta upon r t. Okay, fine. So this is the current per unit area at the interface. Okay, now this is, if it is positive, okay, that means the current is flowing from the electrode to electrolyte, right? Or I can just E, and this is either P or K, sorry, P or N. Okay, so if it is current is positive, means the current is flowing out of the active particles. Okay, and if it is negative, that means the current is inward, right? So here also, as I told you, there are both the things are happening, right? So one of this is a oxidation current. The first term I naught into the first term implies oxidation current, and this one implies the reduction current. Okay, so this is the oxidation part, and another one is the reduction part, right? So it depends which one is dominating, right? Now beta is just some kind of constant. Typical, most of the cases you will see the beta value is taken as 0.5. That is quite a standard, unless until very rarely you will see some other value that is being taken. The F is a Faraday constant. Okay, so F is a Faraday constant, and the eta is known as over potential. Okay, so the over potential is phi k minus phi e minus open circuit voltage of that particular electrode at that particular concentration, right? Fine. Okay, now one more thing is, this reaction in general, or actually any chemical reaction, is governed by what is known as chemical potential. Okay, so chemical potential, if you know, is a quantity which is related to the Gibbs free energy. So if I take the derivative of the, so it's a Gibbs free energy per unit mole. Okay, the chemical potential, because some of you might be from the thermal background, so you can relate the chemical potential easily with the Gibbs free energy, right? Now any chemical reaction will take place, so for you can calculate this chemical potential for any chemical species. Okay, so now a general, let's say the chemical reaction is A plus B C plus D. Okay, so they are some kind of reactants in a chemical reaction. You can calculate the chemical potential of A, you can calculate the chemical potential of B, and you can add it up, right? So you can calculate the total chemical potential of these two things. You can calculate the chemical potential of these two things, right? Only if the chemical potential of the product is going to be less than the chemical potential of the reactant, then only the reaction is going to go in a forward direction. Okay, so the chemical potential play a crucial role. Like in mechanical engineering, like most of you are from, I think, from the mechanical engineering or the physics domain. So in general we say, right, that the system is trying to minimize its energy, right? That is the general principle we use. In thermodynamics we say that it is trying to minimize the overall free energy or Gibbs free energy, right? So here also the reactant actually will try to, the chemical reaction actually is moving in the direction where the chemical potential of the overall system is actually kind of decreasing, right? Now why I am telling you this is because the chemical potential, the total chemical potential is actually mu naught R T ln concentration. Okay, sometimes people write it by divided by the C ref, anyway that is fine, plus Z charge number into F into phi. Okay, fine. So this is known as in general electrochemical potential. Okay, why electrochemical potential? Because of this final term. Okay, so the Z, the small z is the charge, right? For example, Li plus, for that the charge number is going to be 1. Li, in case of Pf6 minus, again the charge number is going to be 1, minus 1. In case of electron it is going to be minus 1, right? So, and F is the Faraday constant, again phi is the electric potential, right? So what you can see from this relationship is the overall electrochemical potential of a particular species is going to be strongly affected by the potential, right? And this, so this tells you that actually by controlling the potential you can change, you can control the this particular reaction, whether it is going to be moving in. So if you see this one, right, this is not going to get affected because the charge here is 0. This has a positive charge, so Z equal to 1. So the lithium plus ion chemical potential, electrochemical potential is going to get affected if you change the potential, right? And electron potential, chemical potential is also going to get affected once you change the potential, right? So you can actually change the potential, right, by changing the electrochemical potential by changing the overall phi, and that's why you can control whether you want the direction in the forward or in the backward, right? So this plays a very crucial role, right? So that's why when we have to charge the battery, we flip it. The positive electrode, we put the negative potential, and now it is actually, when we are putting the negative potential, then the phi is becoming negative, Z is negative, and then the electron potential is going overall up. Like value of the phi for the electron is, sorry, value of the mu for the electron is going up. Okay, fine. So this actually gives a lot of intuition. I'm not going into too much detail, but this is a very important relationship if you want to understand, or from the electrochemical point of view, the better, right? And the same thing is reflected in this equation, right? That the overall current is given by this is actually significantly controlled by this over potential, right? So this is phi k, and this is phi e. Phi you are not directly controlling, but phi k more or less you are directly controlling, and open voltage is anyway more or less given to you, fine. And J naught anyway, the expression is there in the slide, right? Okay, so this is what is happening at the interface. Now we have, so the I k dot n k at the interface, right, is equal to the J that I just wrote, because that is happening at the interface. So there is a current which is actually flowing out of the particle, that's why it is there, right? So this is there on the boundary of the gamma on the k, okay, and the reverse thing happened there in the electrolyte. I E dot N E equal to minus J, okay, fine. The reverse thing is happening because there the current is actually going to be like, so the particle, the current is going out, so that's why it's positive for the active particle, but for the electrolyte it is going in, so that's why it is a negative sign, right? So this is the interface condition for the current or the charge conservation equation, right? Now but you have another equation, and that is the mass flux equation. So that's why if you want to calculate the mass flux, then all what you have to do is you have to divide the current by the Faraday constant. So everywhere actually you will keep on seeing Faraday constant appear, because it is actually able to relate the concentration of the species or the flux of the species to the charge, right? And then this is going to be equal to Nk dot, again small n k, and this is again in the electrode, and you have right. So these are the interface condition, fine. Apart from that, you have the boundary condition. So boundary condition I will not touch too much upon, but the only thing I will tell that these boundaries that are there, which are at the top, at the bottom, the current that is flowing out is also 0, and the mass flux is also flowing out is a 0. So at this boundary it is going to be I tilde k dot nk equal to 0, and k tilde dot nk also going to be 0. The same way it is going to be here for the electrolyte, which is going to be I tilde E dot n E equal to 0, and the n E tilde dot E, right? Because there is nothing is coming out at the bottom, at the top. Fine, okay. Nk is the normal to the domain. Okay, you are only computing the, like in this case, right? You have the condition on the q dot n, where the n is the normal. Here also the n is the normal. Last thing we can discuss is on the potential, the boundary condition, because you have another variable to solve apart from the concentration, that is the potential, right? So the boundary condition is so what will be the boundary condition? So let's say this is positive electrode and this is negative electrode. Sorry, this is negative electrode. So what will be the phi value here? Whatever you are prescribing, right? So especially so that will be like P equal to 4.2 volt if it is a potential driven problem, right? If it is a charge driven problem, then rather than being prescribing the potential, you will prescribe the current. So then you will prescribe the total current that is actually at this boundary is going to be del phi dot n, and then you will multiply with the sigma E, right? And that is you are going to integrate over the whole domain, right? And this you will actually will be equal to the applied, okay, okay, I applied, okay. So that you take the del phi dot n and take the current at each point, integrate the total current, and that should be equal to the applied current, right? Apart from that, it is slightly tricky. This will not be enough if you can understand. If you know the theory slightly well, it has to be at the same potential. So it is at the same potential, and but the potential value is not known, the current value is known. And here on the other end, it is very simple. You just take the phi equal to 0. Right? Now, in terms of initial condition, you prescribed the concentration value Ck equal to Ck naught at t equal to 0, and similarly Ce equal to Ce naught okay. Will we need initial condition on the phi? On phi, do we need the initial condition? Okay. So these are the equation, right? So do we need the initial condition on the phi? So this equation and this equation, are they same or fundamentally same, or they are different? There is a difference, right? This one has a time derivative. So this is the transient PD. So you need the initial condition in terms of the concentration. But this is not a transient equation, right? So there is no time derivative there. So you don't need the initial condition for the phi. You only need the initial condition for the C. Okay. Fine. So this now complete the discussion on the microscale part. Now let's move on to the homogenization. Okay. So Dr. Jain was telling me that he has covered little bit on the homogenization on the thermal part, but let's quickly go through, and if maybe in 2-3 minutes, and then we can move on to the battery part, right? So in general, what is homogenization? Do you hopefully you understand it? So let me just repeat the argument on the homogenization. That maybe I give you one strip which looks so for example, if I see this mobile cover, right, on the top of, if I just see from the naked eyes, it looks homogeneous in nature, right? It looks like things are uniform with respect to the spatial length. Me, if I take the material composition at this point, it looks more or less same, right? It looks like there is no difference, things are uniform, right? But maybe if you zoom out, so if you take a point in the domain and you zoom out there, actually you may see it is actually made of the different combination of the material. It's just that you are not able to see it. Okay. In case of thermal field, we do use what is known as composite kind of material. For example, you know that PCM, phase change material, has a lot of good energy storage capacity, but they are poor conductor of the heat. So a lot of time we use what is known as metal PCM composite. That means you have the metal along with the PCM, right? So for example, you may have some kind of metallic fins, and overall other place you can have the phase change material. So this is now the material is actually combination of the two, right? But when I want to analyze this system, then let's say I want to uh, understand that if I apply some temperature difference T2 T1, how much the heat is going to flow, then I know that the heat flow is minus K dt by dx, right? So but what should be the K? What? Because at some point it is K1, some point it is K2, some point it is K3. I don't want to deal with the microstructure detail. I don't have the computational resources that I can resolve each of these things, right? So what I want to do is I want to replace all this with a homogeneous system, right? I want to work with the that, right? So let's go to the nodes and maybe, right? So I have K1, K2, K3 and so on, and I want to replace this with the uniform K effective, if you want to call it. So this is homogenization. So the homogenization, if I simply define, it is converting a heterogeneous domain, which is actually heterogeneous, into a homogeneous domain. That is what is homogenization. It can be in a structure problem, it can be in thermal problem, it can be in fluid problem, right? But this is what the homogenization in any field. Okay. So do you know how to drive the K effective? No. So how do we drive it?
Add the by applying the energy U1 plus is equal to
No. No, you are on a right track, but I want a slightly better steps. Exact step that I can write and give the answer. Hmm? Okay. So if I will assume that there is a Q that is flowing in the system, right? And Q is going to be same in all the blocks, whether K1, K1, K2 block, K3 block, K4 block, right? The heat cannot, like whatever is the heat, because right now we are assuming the steady state, right? So whatever the heat that is coming in has to go out, right? So then the Q is minus K1. So this is, let's say, T1, this is T2, and this total length is delta x. So then it is going to be T2 minus T1 by delta x. If I do the same thing for the second domain, then the Q is going to be minus K2 T3 minus T2 by delta x, right? Clear, right? And what I can do is I can take this K1 from here to here, so Q upon K1, K2 from here to here to Q upon K2, and then I can add all these things up. So then it is going to be Q 1 upon K1 plus 1 upon K2. There will be lot of cancellation, T2 will cancel like this. So let's say the final one is T10, so then it will become T10 minus T1 divided by delta x. Okay. So the Q is going to be T10 minus T1 length. Okay, so the length is, I assume the 10 block, so it is going to be delta x into 10, right? So length L and 10 here, and that is going to be 1 upon K1, 1 upon K10. Okay, so the effective conductivity is going to be 1 upon 0.1 upon K1 plus 0.1 upon K2, 0.1 upon K10. Right? It is a very simple derivation and you can drive the effective conductivity. Right? It is a very simple arrangement, that's why you are able to drive it. In case of complicated arrangement, there are special computational technique. The homogenization is a field in it itself. Okay, so one of the PhD student is doing with me working on the homogenization, but we are working on the structural aspect, not on the thermal aspect there. But so it's actually quite mathematically involved field, but anyway, we will not go into those things. But at least the central idea of the homogenization hopefully is clear, that I want to convert a heterogeneous domain into a homogeneous domain, right? And at least for simple system, I can drive the effective properties very easily, right? But if I give you a complicated system like this, I give you that this is the underlying system, this has the conductivity K2 and this has the conductivity K1, it is not that easy, right? Then you have to do the computational homogenization. You can make RV and all those things, anyway I will not go into those things. So that, yes.
So in my research seminar,
Uh, uh.
I will talk about exactly this problem, where you have multiple inclusions of different properties compared to the background, and how do you solve such problems analytically?
Okay, good. Not numerically. Okay, so I know the things numerically, but it will be good to see the things how to solve it analytically. Okay, so I think after Dr. Jain lecture, you will become, it will you will become to know, you will come to know much more about this. Okay, fine, good, fine. So let's move on to our battery stuff. Right. So for those who are working even remotely on the mathematical stuff or other things, I always say, at least to Kulbhushan, do not assume the things are in series or parallel or whatever it is. Always drive it. Even now, I drive it. Right. So I'm saying, even if you know the final answer, keep on. It takes 3-4 minutes of effort. But if you keep on doing this kind of exercise, things remain with you. Otherwise, you become out of touch very quickly, right? Otherwise, you just lose the gist of the main concept, and all you remember is some formula, right? So always, at least for some simple things, start from the basics and drive the things on your own. That helps in overall thinking. Okay, so everything is there in the book or on the web, on the Google or in the Chat GPT, right? But in order for these things to go inside your head, you have to work these things over and over and over again. Then only you can actually use them in your research effectively. Right. So now this is, now if you see this picture, it has completely changed. Rather than this beautifully looking electrode, now it's a boring uniform picture, right? Because there is a homogenization of the domain that is carried out. I am not no longer trying to resolve the heterogeneities at the micro scale and carrying out the things, right? So how do we carry out the homogenization? Actually, for homogenization, at least for whatever we are going to cover, it's a fairly simple thing, but still we need to do that. So let's do that. Okay. But at least this picture is clear, right? What we are doing, we are replacing all this heterogeneity with the homogeneous domain. Okay. So again, we'll do the same way that we have done for the microscopic model. What will do is we start with the electrode and we'll move to the electrolyte. Right? again we have the 4 species to take care: lithium and electron in the electrode, and the lithium plus ion, and the charge or the anion in the electrolyte. The same 4 things we'll take care and we'll solve it. Okay, so let's do that. And good. So yes, so let's first work with the lithium in electrode particles. Now the funny thing is, after talking about all the things about the homogenization, you cannot do the homogenization for lithium movement in the battery. Okay, that is not possible, because the lithium diffusion is actually happening at the micro scale. Okay, so what is happening here when I am converting this K1, K2, K3, right, into this homogenized field? That is fine. I am actually simplifying my problem, right? But I am losing some detail. If someone want to know that how the temperature is actually varying in these interfaces at the K1, K2 boundary, I cannot tell. Right? I have lost this kind of detail that is no longer available with me. So if there is some phenomena which is happening at this length scale, and if I carry out the homogenization, you cannot expect me to find the answer for that particular phenomena. That is not possible, right? So the lithium diffusion is actually happening at the particle length scale. So we cannot do the homogenization for the lithium movement, right? So there we will stick to our normal equation, and that was del Ck over del T plus divergence of the Nk equal to 0. Here I will write in the subscript capital X, and the reason I am writing the capital X is to tell this capital X is to denote that things are happening at the micro scale or at particle level. Fine. Okay. So for each of those particle, you are still solving this equation. Okay. But only this equation, the rest of the things will do the homogenization. Only one equation we actually keep it as it is. Okay. So I will go to the slide. Right. So this is for the electrode modeling slide. So if you see this first equation, you see the capital X, right? That is because I am actually sticking to the micro length scale. This is the overall domain, how I will solve this equation. So these are electrode particles. The black things are additive particles which are not playing any role, right? So, and the white thing is the electrolyte. Right? So if I am solving this particle, right, all this is the boundary, right? So on the boundary there can be three things, right? So ultimately to solve any equation, I told you, you require boundary condition. So here on the particle there can be three things can occur. One, there may be electrolyte that is present. That is one of the things that can happen. The second thing is additive particle may be present. That is the second thing that can happen. Another thing can happen, it is a part of this boundary, the domain that I have taken. These are the only three possibilities, right? Either at the boundary you will have the electrolyte, you will have the additive particles. Third, you are going to have a boundary of the domain, because I am taking at a time, I am just taking some small domain, right? Fine. Okay, is clear? Right. So now, right. So in case of additive material, these are inactive material. They don't do anything. They don't lay. You can lithium is not going inside this, right? So lithium is not going inside it. That means where is there this additive material, the flux is actually equal to 0. Right? Nothing is going out. They are just as there as a glue. They are not doing anything. So that's why the flux is 0. The other thing that is there, that is similar to the previous one, that the flux is equal to the current divided by the Faraday constant, right? So n tilde dot nk equal to the jk, the current that we just saw, Butler-Warmer equation, divided by the Faraday constant, that will give you the flux. And on this boundary, because these are not actually domain actual boundaries, these are only some portion of the domain that you have taken. Actually the overall electrode is much bigger, right? So these are artificial boundary that you have taken for the computation, right? So in this boundary what you do is you actually take the periodic boundary condition. So to denote that this is actually a much part of a much bigger domain, I will not go into too much detail of the periodic boundary condition, but the periodic boundary condition means whatever is happening at the top edge is happening at the bottom edge, whatever is happening on the left edge is happening on the right edge. So whatever is the concentration of the top edge is happening at the bottom, the top edge, and the, so if I take this point, the concentration here is going to be same as the concentration here. The concentration here is going to be same as the concentration here. The concentration here is going to be same as the mirror image version of that on the right hand side. Is it clear? Right? So these are known as periodic boundary condition. Again, the periodic boundary condition are not used heavily in homogenization field, whether it is a thermal homogenization or it is in the structural homogenization or whichever kind of homogenization it is. Okay, fine. So this is the, these equation are known as particle equation because you are solving now at the particle levels. Earlier we don't need to give them a special name because everything is happening, we are resolving at the micro scale, but now we are working at a different scale. So here we add the disclaimer that these equations are solved at the particle level, and that's why we are calling them as a particle equation. Fine. Okay. Geometry. Hmm. Hmm. No, so if you know, if you have this diagram, you can always generate the mesh, right? The main thing is how do you get the actual image of the electrode? That is very difficult. So I think they do some kind of, if I am not very sure, but I think X-ray tomography or something they do. There are some experimental technique which can actually look into the electrode and actually can give you the size distribution, overall size distribution, that how what is the overall. So generally you get the overall size distribution, and from that you try to model it. You don't know actually, you don't try to actually take every particles exactly how it is there in the actual battery. Even if you are trying to model the things in a great detail, what you do is you actually do some kind of experimental observation through this X-ray tomography and other things. You get what is the overall size distribution, and then you try use some computational technique which will randomly generate the particle following that particular size distribution, and then you do the model. Okay, fine. So this can we take this? Manshu ji can. अच्छा तुम्हारा thanks. Is it clear? Any other doubt? Okay. Now in the electrolyte we are going to do the things. Or yes. Actually we can do the charge conservation here. So the charge conservation is going to be simply del dot I equal to no, that is not going to be there. 1 second. Let me do that way only. We can do that. or we can, okay, just let me look at the notation, give the same notation. So bj I'm taking. Fine. So this is, so have I modified this equation? So now this is the homogenized version of the equation. You see something has changed, right? What has changed? Earlier on the right hand side I had 0. Now I have some non-zero term, that is the known as source term. Right? So what I am doing is कि whatever is happening, so the current is generated at the interface. Right? What I am doing, I am replacing this with a homogeneous field, right? And this J which was there at the boundary, I am saying I am not taking care of the boundary. Now I am distributing the overall current in the domain, and I am simply calling this as a J. Okay. So I am converting the boundary information into a overall volumetric thing. If you are confused with the current, the best way is to try to connect the things with the thermal. Okay. So consider the case where there would have been some kind of heat source. So some kind of heat is getting generated and only at the boundary, and I want to solve this problem. Okay. So what I will do, but I don't want to resolve these boundaries and everything. I want the fairly approximate result. That is fine with me. So what I will do, I will calculate the total heat that is generated, right? And I say that, so the total heat generated, let's say, is Q, right? Then what I will do, I say that I will divide this with the total volume of the domain, and this I will use as a heat source. I will assume now, in actual the heat is generating only at the interface, but I would say I don't want to resolve the interface, so I will assume that uniformly the heat is generated in this way, right? So this thing I convert the boundary thing, which is the area thing, into the volumetric thing by considering as a source term. Now the domain is homogeneous. Okay, and the I now is given by minus sigma, but this is actually homogeneous quantity into del phi. So this conductivity is different from the usual conductivity, because now this is a homogeneous conductivity, because the domain is consist of the electrode particle. It is also made of the binders, which has a very poor conductivity, right? So now combining all these things, I will find through either experiment, through some analytical technique, or from the numerical technique, the effective conductivity, and then I will put this into this equation. So this is not of a specific material, this is the overall effective conductivity, right? And now this boundary term has been changed to the this one, to the volumetric thing, right? So now let me show you the equation, and if I miss something I can do this way. So this is electrolyte domain. Okay, I thought I have done. Okay, right? So this is Ik equal to minus sigma k del phi k. Again, just repeating this J. If you see this expression, what I am doing, I am calculating, integrating it over all the part that is actually in touch with the electrolyte, because there only the current is flowing, and then dividing with the total area, boundary area of the particles. This will give me the J of k, and this B that I have, that is the percentage of the places where I have this boundary. Of the total boundary, how much of the percentage is the boundary between the electrode and electrolyte. Okay, fine, because this I am computing it everywhere, right? So that's why I have to divide by that then. Okay. Fine. So now moving on to the next one. Okay. Okay. So the electrolyte again we have will again do the homogenization, right? Now there is a one thing, there is going to be small difference compared to the previous one. So the overall domain is a heterogeneous domain. Only the part of it is occupied by the electrolyte. Right? Let's say the fraction of the part or the porosity of this is epsilon. Okay, only the some part of it is actually carried out by the electrolyte. Right? If I take now, I want to do the conservation of the lithium plus ion. Right? So when I am taking my domain for the conservation, right? Then what will be the total amount of the lithium plus ion? We saw that, right? The um, this is going to be C lithium plus ion that we saw in yesterday plus, and then we have to integrate, right? But then this is the total volume, right? But I don't have the total volume available for the lithium plus ion. I have only the fractional part of it available to that, right? So if the porosity is phi, the actual part that is available is only phi into dV, right? If the porosity is 50%, only the 50% can be occupied by the electrolyte, right? Otherwise it is not going to be there. So to account for that, I put the epsilon there, and then again the same thing del by del T, and that is going to be equal to the minus of the flux, and that is going to be the N lithium plus ion and dot N equal to ds, right? Again I do the same thing, apply the Gauss divergence theorem and everything. I get the equation which is going to be epsilon del C Li plus by del T plus divergence of N Li plus equal to 0, right? This is if there is no source term, right? Without source term, right? But we have the source term, right? Because there is a flux of the Li plus that is there. Earlier when we were modeling the micro thing, we wanted to resolve the interface. That's why we didn't took it as a source term. But now we don't want to do that, right? So the source term is going to be again Bx, which is same as previous. The source term is similar, again J, that we have calculated J average, and then divided by the Faraday constant, because again we want the number of moles, not the charge, right? So again the similar kind of thing. So now if you see, this is epsilon del C over del T, divergence of the flux, and now this is the source term which is B into J divided by F, right? And in case of current there is no F, otherwise the source term is same. And then these are anyway boundary condition, will come to that later. The these two equation is same as yes micro scale. The constitutive equation is same as micro scale. The again the similar thing. This dE and sigma E are no longer the diffusion coefficient of the electrolyte or the conductivity of the electrolyte. This is again the homogenized property, because you have done the homogenization, right? There are hindrance, right? If for example, 1 second, this is the electrolyte, I have the lithium ion plus here, it want to move and go to here, it cannot directly move, it has to go and take a very tortoise path and go there. So the resistance to its movement has been significantly altered, right? So that's why these properties, the diffusion coefficient, the conductivity, everything is an effective conductivity, effective diffusion coefficient. They are not specific a particular material property. These are homogenized property now. Okay, fine. So now in case of homogenized, if we summarize the things, in case of lithium movement, things remain as it is because we have not done any homogenization. For other things, there is a homogenization that has happened. What it has done is, it has converted the area terms into the source term, and these kind of source terms are appearing now into the equation. So because now this has become into the volumetric quantity, and apart from that, all the properties such as the diffusion coefficient, conductivity, they have been converted into the effective properties rather than being a specific property of a specific material. So this is kind of in a very broad sense the summary. Now this excellence, I told you electrolyte is everywhere. So if this electrolyte is in the negative electrode, then you will take the epsilons to be the porosity of the negative electrode. If this electrolyte is in the separator, you will take the porosity of the separator. If this electrolyte is in the positive electrode, you will take the porosity of the positive electrode. Right? Now, same thing with the B. Sorry, this keep on happening. Right? Same thing with the B. Now you see this one, GIAN, which is the current density in the negative electrode and in the positive electrode. What should be the value in the separator? 0, because there is no current that is getting generated, there is no active particle there, so that is going to be simply 0. So the equation is, now it is a uniform equation where the electrolyte you are solving of whole battery, positive electrode, negative electrode, and the separator part. The only thing is, the coefficient that are appearing in the equation is different for the different domain.
The terms JN and JP,
Huh.
do they come from the equations in the electrodes?
Yes, they are coming from the Butler-Warmer equation. That does.
Everything is hopelessly coupled with each other.
Yes, yes, and that is actually, if you see, just on this point, if you see in the numerical community of any literature in general, at least 50% of the paper, if you go to the core computational community, 50% of the paper will be where people have written their in-house code. Okay, battery literature is the only literature, at least in my limited career, I have found where most of the people uses COMSOL. They don't try to write their own code. Okay, the reason can be, it is really difficult if you if someone is from the computational background and try to imagine they have to write the code. There are particles, for each of these particle you are solving the PD, right? And now there is an electrolyte equation that you are solving at the homogenized domain, and each of these particle equations are coupled with this one, right? And all these are non-linear PD, these are not even linear PDs, right? They have, and the J is given with something which has an exponential term, and the potential is coming in the as a power of the exponent, right? It's a highly non-linear PD, and now you are solving everything together. It becomes really at two different length scale. So as a understanding, it is fairly still, I would say, compared to, I would say, implementation, it is still simple. If someone has to really implement and start from the scratch, it is really an exercise itself. It will take, I think, 1 to 1.5 years.
So I was actually thinking of trying to solve such problems analytically.
Okay,
You were saying that even the numerical implementation is so challenging. Solving these analytically is probably near impossible.
Yes. So there is only one paper I found, I think, where they do lot of linearization.
Yes.
So they do linearization. They have converted the system into the linear form, and they have taken lot of assumption. I can share the paper with you. So they have, what they have done. It's the paper is in a very different direction. They want to find out the transfer function of the overall domain. So they have done a lot of assumption. They have taken that the Butler-Warmer equation also they have done some, I have not understood all the details, but they have linearized all the system and they are able to drive the overall transfer function in terms of this diffusion coefficient and all those things. So they have given the nice closed form expression at the end of the paper, and they have actually given the assumption, at least the result they are showing and the validation they are showing, that is actually fairly decent.
The main non-linearity in this problem comes from the Butler-Warmer.
Yes, yes, yes.
Apart from that, the equations themselves are fairly linear.
Yes, only the length scale is different. And the one is at the micro scale and another is the macro scale. Otherwise, non-linearity as such is not there. I think there can be, this one is slightly non-linear because the mu is dependent on the log of the C. But again, maybe you can linearize at least in the small concentration you assume, and you can linearize this term. Should not be that difficult. Linearization you can do, but actually it's a non-linear term. But you can, but the main thing is the Butler-Warmer equation. That is the main activity. So I will share you the paper and maybe if it helps, right? I don't know. This is annoying a bit. Fine. So this is the equation that we've solved. And in terms of the boundary condition, if you see the flux is 0. So I will go back to this one. So even if you don't, if you have not understood the mathematical part of it, that is fine. But if you see intuitively, the main part is, if you want to drive later the boundary condition for yourself, the main thing is when the current is flowing at the current collector, all the current is flowing through the active particle only. No current is passing from the electrolyte to the current collector. That is the one thing that you have to remember. If you remember this thing, then you can write the boundary condition yourself, right? So that's why if I am in the electrolyte domain, then the del phi dot n is going to be 0, right? Sigma del phi dot n is going to be 0 because there is no current that is flowing out from the electrolyte. The same thing happened at this boundary, right? Once you understand this particular thing, then it is fine. So once you understand at each point in the domain which is contributing to the current, are the electrode is carrying the current or the electrolyte is carrying the current. So if you see this boundary, right, all the current is carried at this boundary by the electrolyte, right? Electrode particle job is done before this boundary. So from here the current is carried by the electrode also at the electrolyte also. Here till here, so here electrode is 100%. Slowly electrolyte is 100%. Till here electrolyte is 100%, and slowly electrolyte reduces, and it becomes 0 here. Okay. Once you understand that, then you can always write it. But that is the main thing that you have to understand, that which one is carrying the current where. Then it is fairly okay. Fine. So I think we are done with the homogeneous model also. Right. Now we will go to the last one, which is, at the end of the day, nobody, in I think 99% of the people, or even 99% probably will be underestimation. Don't use microscale model or the homogeneous model. They use what is known as P2D model. But in order to arrive at the P2D model, you should know all these things. But at the end of the day, generally we use the P2D model. Okay. So again, so what is the P2D model? Okay. So what it is doing, it is making lot of assumption about the nature of the battery. Okay. So this model assume, first of all, that all the electrode particles which were having earlier funny looking shape are no longer funny. Now they are boring spherical object. Okay, the nice spherical object. All of the particles have the same size. So things have become much less interesting because things are uniform. So at least for a person who is working in the numerics, it becomes a bit boring. But yes, but it becomes much more doable. Okay. So and you assume that this, if you see this earlier I was showing you 2D domain, right? Now it has become 1D. Right? So you are assuming that the things are uniform along the y and along the z, anyway we have never considered. So along the y now the things are uniform. So it's like this row is getting repeated uniformly at the top, right? So now the things have become 1D. There is nothing is moving. The current is not flowing in the y direction. Everything is only flowing in the x direction. It has now become a unidirectional case. And the particle has become uniform. Rn is the size of the negative electrode and Rp is the size of the positive electrode. Right? So the problem has simplified lot. And why the problem has simplified? Because earlier for the battery either I was solving a 2D problem or 3D problem. Now I will be solving only 1D problem, which is computationally much cheaper compared to the 2D or 3D counterpart. Right? And the particle also has become now is spherical, right? So rather than here in case of particle also, so I think Dr. Jain mentioned today one problem, right, where he was showing the conservation of the heat in the radial coordinate, right, in the cylindrical coordinate. So the same thing you can do here, right? So you can go to the polar coordinate and work out the things there. Fine, and so I guess so I will reduce my effort little bit. So these are the particle equation. Now you see only the derivative is appearing is the r, because things are only changing as a function of the radius. Now there is no longer x and y, so it becomes nice. Only independent variable that I have is r, which are much easier to solve. It is still two variable r and t, but at least in the spatial coordinate I have to deal with only r. So this is the particle equation it becomes. So it is a similar thing, only the grade is getting replaced by the del C over del R in some way, nothing much. And if you see the electrolyte equation, earlier I was having the grade of phi, gradient of the phi, now it has become only del C minus del phi over del x. Right? So it has become much simpler. Right? And otherwise fundamentally it is same. Right? The condition also I can write boundary condition only out of one point, because in the 1D the boundary is a point, right? So boundary condition also become very simple. The on x equal to 0, phi n equal to 0, and all these things. So at x equal to 0, phi become equal to 0, in equal to 0 at x equal to ln. So as I told that at x equal to ln, the all the current is actually taken care by the electrolyte, so the electrode will not carry any current, right? So that's why in is the current carried by the negative electrode, right? So that becomes 0. The same thing on the positive side. So now these are the equations which are much simpler compared to the LN. But in order to understand P2D model properly, you have to start with a microscale model, then you go to the homogenization, and then you make some assumption about the nature of the particles. And once mainly you are assuming all the particles to be uniform of the spherical size, and then you are done, right? Fine. So this, there are two names to this. One is DFN model. I don't remember the full form of DFN. That is the name of three scientists who actually developed this model. The last one I know, this is a Newman. Okay, this is, he has done phenomenal work in the lithium ion battery. His papers are, I think, around 1980, if I am not wrong. Those are like still the landmark paper. All of the battery computational community will refer his paper only. Right? And P2D model is pseudo 2D model, because it's not actually 1D, because it's not only x, you are solving in x as well as in the r, but it's not 2D actually, because r and x are not actually strongly coupled. It's not like x and y. So that's why it's known as pseudo 2D model. Okay, fine. So it's sometimes people call it 1.5D model, whatever. Okay. So what is the time and what is Okay, I was saying I will leave early.
sugar,
हाँ. Okay. Hmm. Hmm. Okay. Fine. So I will just take 5 minutes. So this is uh, taken from the literature only, but I think Kulbhushan did some of this analysis himself. So I just want to show some of the output so that you get feel that after doing all this work, what kind of plot we generate. Okay. So this anyway we know. So now I just kept this thing that how many parameters you need to run the simple P2D model. Okay, it's just the last one was simplest, was so simplest I didn't give more than 5 minutes. But if you have to run it, this is 15 parameter, another parameter 38 roughly, and these number of parameter you need. And if you are working in the battery modeling, one of the biggest challenges to find a paper which lists down all these 38 parameter in a proper detail.
For the chemistry that you are working on.
Yes, they don't no. They will show the validation with the experiment. They will list 30 parameter, but somehow they will always miss 4 or 5 parameter. Now it becomes a challenge to reproduce their result because you are keep on figuring out what those 4 or 5 parameters they have taken.
Yeah.
And I think at least Kulbhushan has spent around 5 to 6 months figuring out those parameters itself, and so we keep on trying to model, and then we give away. Okay, now this paper cannot be real, cannot be reproduced. Now let's move to another paper who has given this 38 parameter. Because even if 1 or 2 parameters are given, it becomes very difficult to actually reproduce their result. While Newman, the first guy who did it, you see their paper, his paper, is phenomenal, very nicely written. Everything is there in a proper detail. Right? Now, cherry on the top, this conductivity of the electrolyte is a function of the concentration of the ions. So you don't need only a number, you need this whole expression with lot of unknown constant to determine, or you can take it from the literature. This open circuit voltage is also a function of state of the charge of each of this electrode. Again, those data is available in the experiment, from the experiment in the literature. You can refer to that, but I just want to show this like that. It is a humongous task to actually really exactly nail down the even the P2D model. Okay. This is known as Bergman relationship. So effective properties are function of directly the porosity. So you don't need to carry out the homogenization everything. You can just simplify this. The effective properties porosity to the power 1.5 into the actual conductivity. Okay, I will not go into detail, but if you don't want to take the trouble of homogenization or something, these are simple empirical relationship which works to a decent degree. And right, these are, so he has taken lithium, I think graphite as a negative electrode, and this magnesium oxide as the cathode, and this is showing the open circuit voltage as a function of the SOC, that how it is not constant. When it is actually fully charged, then it's a 4.2. So here it is SOC is equal to 0 at the negative electrode, sorry, at the positive electrode. At the negative electrode it is SOC equal to 1, so it is going to be, here the open circuit potential is going to be 0, right? So then, because the open circuit potential of the battery is positive charge, open circuit voltage minus the open circuit voltage of the negative one, right? So this is how it is varying with respect to the SOC. Again, based on the paper, you will see different. There will be some variation in the result. So this is the final outcome of the simulation. So generally, this is the first thing that you report. So this is, I think, if I am correct. Um, okay. So this is the discharging curves. Okay. And so here the battery is fully charged, and this is the amount of the charge it has given, right? So it has given total So the theoretical capacity of the battery is roughly around 1.8 mAh per centimeter square. So if I am this, so this is the first one, the red one is the, if I am discharging the battery at a really slow rate, 0.1 C, right? And the last one, when I am actually discharging the battery at the 4 C rate. You can see that theoretically the battery capacity is roughly here, but when I am discharging fast, the actual capacity of the battery is actually now become only the 50% of the actual battery. Right? So the charging rate or discharging rate considerably affect the battery performance. So that's why you want to actually do the modeling. You want to understand how the battery is going to behave in a different charging discharging rate. What will be the voltage that I am going to draw? I cannot, when I am designing the battery pack, I cannot just assume that I am going to get 4.2 voltage, because as you can see, 4.2 volt I don't get. As soon as the battery start discharging, my actual voltage drops, and that is fine, but the more trickier part is that this actual voltage depend on the charging and discharging rate. No, open circuit voltage is a nonlinear function of the SOC, but the open circuit voltage was given by the previous slide. By this one. This is not the open circuit voltage. This is the actual voltage right now you are driving at a given load. This is the terminal voltage. This is not the open circuit. This is also similar. Only thing is there is some kind of residual resistance. So Dr. Jain in the morning was talking about this SEI film. Right? So all this molding that I told you was assuming there is no SEI interface. There is no lithium plating. Right? There is no double. There is a capacitor double layer. All these phenomena I didn't discuss. But if you have try to incorporate those things, the first thing you generally want to do is you try to incorporate the resistance offered by the this SEI layer that makes it at the particle um, interface, right? So there the voltage, because there is an additional voltage drop in overcoming the resistance of this SEI layer, there is an additional voltage drop that you can see, right? And this is with respect to the Bergman coefficient. Because I have not gone into too much detail, I will not go there. And this is also fine. This is the one that I will show. So this is the concentration of the lithium ion in the electrolyte. Okay. So this is the negative one, right? And this is the positive one, right? Actually, I want, right? At this at the end of the, when I am not, the voltage had dropped significantly, right? It's no longer functioning, right? So now if you see this blue one, right? Here everywhere there is the presence of the lithium ion, right? But if you see at higher charging or discharging rate, this green one, there is a lot of lithium that is there in the negative electrode, right? But if you see to the positive electrode, it is not there, right? So what is happening in the battery? We have seen there are so many diffusion coefficient, right? What does the diffusion does? It is actually slowing down. If the diffusion coefficient has a finite value, right? So this diffusion phenomena has its own speed, right? So if you're trying to draw the current too fast, right, and the diffusion, the overall kinematics of the battery doesn't allow drawing of the current that fast, then what is happening? That process is slow. It's not able to actually, the lithium ions are not actually able to overcome that resistance in a way that it can actually deliver at this particular speed, right? So that's why actually you see that this way. Right? Now the funny thing is, if you stop the battery, right, you stop drawing the current and you let it settle for some time, then what will happen? So right now voltage is almost 0, or let's say 2.2 or something, it is not usable because the voltage has dropped at least some, it is below 2 or around 2. Right? Now if you leave this battery for some time, now what will happen? This lithium ions will have some time to actually go from the anode to the cathode, right? And then the battery will recover some of its potential. Right? And again, maybe you can use it for some more time if you want to use it, right? So this actually means I like this plot quite a bit. So at least to me, it explains a lot of things about that, how whatever we are learning in terms of the diffusion coefficient and everything, how does actually they affect the things at the end of the day, right? I think by solving all those partial differential equations. So everything was in the. No, I have not calculated. So these all partial differential equations are hard coded in the console, and we are using the console to generate this plot. Okay. So there is another software, by the way, that is known as PyBEM. This is a Python based solver, open source solver for the lithium ion battery. This is, I think, European. There are some couple of universities which are actually leading the development of this uh, software PyBEM. It's a Python based, freely available battery solver. Okay, I have not used it personally, but I think given the kind of, I think Imperial University and Imperial and other universities are involved. You can check it out. And this is anyway not that important. Okay, so I will probably end with this slide. So again, Dr. Jain was mentioning today in morning Arrhenius equation. So in general, whatever the constant, although we have not touched upon, so this we have just seen the electrochemical modeling. We have not discussed the coupling of the electrochemical, electrochemical, with the thermal thing. But just to stress upon all the things that we have taken, diffusion coefficient, conductivity, each of these parameters do depend on the temperature, right? So in general, if you have some explicit relationship with respect to temperature, that is well and good. But if you do not have some special relationship, in general the by default choice is the Arrhenius equation for all the parameter in general. That is the by default one, unless until you have some extra information or something. So what I wanted to convey ki if you want to understand the thermal modeling and you want to do the other thing, even that thermal modeling, the temperature values will affect this electrochemical analysis, because that actually temperature was appearing again and again. If you see the Butler-Roemer equation, there was a term RT. There was a temperature. All these constants are also do function of the temperature, right? So things are quite connected. Electrochemical and the thermal modeling is quite connected, and yeah, so you can do the modeling, and I think time is over. I thought I will actually wind up much faster, but I had actually some extra material which I had the SEI growth modeling and capital double layer and everything, but I think good that I got saved from following that thing.
Industry, most likely you will be using numerical simulation tools for solving problems. Okay, the same tools that are used for solving heat transfer problems are also used to solve other problems like fluid mechanics, electrochemistry, mechanical stress and strain analysis, and so on. And therefore, the stuff that you can learn by doing heat transfer simulations can also be used for solving a bunch of other problems. Okay, so let me start today, and by the way, this is part A. So the tutorial tomorrow will be continuation of what I am teaching today, in order for me to finish up talking about multiple aspects of numerical simulations. So the basic idea is that if I have a simple heat transfer problem, suppose some heat enters this body and the temperatures on the other three sides are 0. I can write a governing equation for this problem. I can say d to t by dx2 plus d to t by dy2 equals 0, subject to some boundary conditions, etc. And I can use all that and my knowledge of mathematics to write an equation for the temperature distribution. It will be double summation CNM sine of something, cosine of something, something along those lines. It will be a messy, long, complicated equation. Okay? But the good thing about that equation is that it is an exact solution. In this equation, if I insert any value of x and any value of y, I will get to know the temperature exactly at that point. Right? And I will get to know the temperature without any error involved in the calculation. Right? Now the problem is that this approach works fairly well for a regular geometry like this. But what if my geometry was like this? Or what if it had a hole inside it? Or, you know, a more realistic geometry like the one you will see in real life will probably not be nice and regular. Most likely it will have some weird, shape, or the thermal conductivity may be a function of temperature, or all kinds of realistic things that throw off this mathematical analysis. This mathematical analysis is truly valid and possible to do only when I have a regular geometry. What do we do if the problem is somewhat more complicated? For that, numerical simulations come to our rescue. So in numerical simulations, roughly speaking, what we do is that we take the geometry of interest and we break it up into a large number of nodes. And we say that, look, instead of finding an equation for the temperature everywhere in the body, all I will do is that I will try to find out the temperature at each of these points Ti, where I would go from 1 to all the way to n, where n is the total number of nodes in my body. So I will not know the temperature truly everywhere. I will only know it at a handful of points on this body. Moreover, this numerical analysis approach will also give us a temperature that is not exact. There will be some error associated with this temperature. Okay? Provided I am willing to live with those two imperfections. The first imperfection is that I don't know the temperature everywhere. I only know the temperature at specific points. And the second imperfection is that even that temperature has some error in it. It's not, I don't know that it is the exact temperature solution. But if I am willing to live with those two imperfections, then numerical techniques allow us to solve these problems in a wide variety of different types of geometries and shapes and sizes and so on and so forth. The good thing is, even though there are these two imperfections that I talked about, I at least have control about the extent of those imperfections. In other words, by increasing the value of n, I can make my solution more and more exact. I can reduce the error to an extent that it may possibly be acceptable to me. As an engineer, if I know that the temperature here is accurate up to 0.01 degrees Celsius, then do I really need a temperature more accurate than that? I probably don't, right? What is the difference between 29.00 and 29.01 degrees Celsius? I cannot even probably measure it that accurately, right? So I'm willing to live with this kind of error. And if I increase the value of n, I can make that error go down even further at the cost of computational time. So the trade-off there is that increasing n will improve my error, but I will have to spend more time or computational resources in doing my calculations. This used to be an important trade-off 30-40 years ago when computational power of computers was fairly limited, but nowadays I have so much power available literally on my fingers, in my cell phone or in my laptop, that I can really ram through these calculations with even a very large value of n. I don't really have to think too hard, for most problems anyway, about computational power. And so that is why numerical techniques have become more and more popular in the past several decades, to the extent that now there are very nice software tools that will do the job for us without us having to see a lot of mathematics, right? So companies like ANSYS and others have figured out that it is best to not show people a lot of equations. So they hide all the equations behind the screen. On the screen you only see a nice GUI where you define the geometry of the problem, you show how the problem works, etc. And after you provide all the inputs needed to solve the problem to ANSYS, then there will be some calculations that will happen in the background, and it'll spit out a nice temperature distribution that you can look at. That is all very good. It makes it possible for people with even very little training to start using numerical simulation tools, but the danger there is that it is a garbage in, garbage out system. If you provided the wrong inputs, it doesn't have necessarily any intelligence at that level to understand that the results are incorrect. It will give you whatever results it produces without any comments on whether the results are probably acceptable or not. That is a judgment that you have to make, and that is where your judgment, your training as an engineer comes into the picture, right? So somebody once told me that numerical techniques make a good engineer great, but they also make a bad engineer dangerous. Okay, because if you design a bridge using a numerical technique and you're not doing it the right way, then I don't want to drive on that bridge. Simple. Okay, so my goal in today's seminar and the seminar next is to provide you two things. One is a demo of the numerical simulation tool itself to show you how things work, right? But perhaps more important than that, I want to give you a brief overview of the mathematics that happens behind such simulation tools, because almost anybody can do numerical simulations. I think what is more important is for you to understand what is going on in the background, so that perhaps you may design your own numerical simulation tools, right? There are people just like you who graduate with a master's or a PhD and then go work for companies like ANSYS and build these tools, right? That capability requires both the core knowledge of heat transfer and fluid mechanics, and also some knowledge of computer programming and coding and all that stuff, right? So I'll start today by giving you a background of the mathematics that goes behind solving such equations, and then I will also begin perhaps today itself a demo of the ANSYS numerical simulation tool, right? So the basic idea behind a numerical technique is called discretization. The idea is that I want to take a continuous equation like d2t by dx2 equals 0, and I want to convert it approximately to a simpler form. I want to take this ordinary differential equation and I want to convert it into a linear algebraic equation. Okay, and for that mathematics comes to our rescue. If I have a one-dimensional body and if I break it up into a number of nodes, node 1, node 2, node 3 and so on, and if I was to focus on the ith node, This is the ith node, this is the I plus 1th node, and this is the I minus 1th node. Then you can show using Taylor series expansion that d2t by dx2 is approximately, it's not exactly, it is approximately equal to ti plus 1 plus ti minus 1 minus twice of ti divided by delta x squared, where delta x is this distance between nodes. Okay? This is an approximation, this is not an exact solution. But what that means is that if the second derivative of temperature has to be 0, then I can say that this quantity must be equal to 0. Right? You can think of this equation as a algebraic equation in 3 unknowns. What are the 3 unknowns? Ti, Ti plus 1 and Ti minus 1. From just one equation in 3 unknowns, I can't solve for all 3 unknowns, right? If I have n unknowns, how many equations do I need? I need, in general, n equations. There are some exceptions to that statement, but in general, I need n equations in n unknowns. So, if I am interested in finding out the temperatures at all the nodes, there are n number of nodes. In order to find out the temperatures at all of these nodes, I need to be able to write n equations. If I can write n linear algebraic equations, then I can solve those equations and find out what those n temperatures are, right? In fact, the problem of solving n equations in n unknowns is a very standard problem in applied mathematics, right? We write it in the matrix form. If you remember, Ax equals b, and from there, and from there x is equal to A inverse multiplied by b, right? And matrix inversion is a standard problem that I'm sure you all have seen and so on. So this is an easily solvable problem, provided I can generate those equations. And how do I generate those equations? Well, it's a community effort. If all of these n number of nodes can contribute one equation each, then we would have done our job, right? So I will go to every equation and I will demand I will go to every node and I will demand one equation from that node. So forget about the 2 boundary nodes for now. Let us start from this node. I go to that node and say, please give me an equation. And that node says, okay, if in this equation I put I equals 2, then the equation is T3 plus T1 minus 2T2 equals 0. Correct? Everyone following me? If I go to the second, if this is 2, this is 3. If I go to the third, I will similarly have T4 plus T2 minus 2T3 equals 0, and so on. I have only gone to the internal nodes. When I go to the external nodes, these two will contribute an equation based on the boundary conditions. Suppose I provide a very simple boundary condition that the temperature here is 0 and the temperature there is 10 Kelvin, say. Then the simple equations that these two nodes will provide are T1 equals 0 and Tn equals 10. Right? So the equations from the boundary nodes will come from the boundary conditions. The equations from all the other internal nodes will come from this discretized version of the governing equation. I mean, why is this equal to 0? This is equal to 0 because d2t by dx2 was supposed to be 0. That was the governing energy conservation equation. right? So I've taken the differential form of the governing energy equation, I've converted it into an approximate algebraic form, a discrete algebraic form, and that is what is generating the n number of equations for me. Once I generate n equations, I can solve for them. If there are only 5 nodes, I can perhaps solve it by hand, but if there are 1 million nodes, then I will leave it to the computer to do the number crunching for me. Okay, I have demonstrated this for a one-dimensional problem, but similarly I can solve a two-dimensional problem as well. So suppose I have a two-dimensional plate and I have a bunch of nodes inside this plate where this node is the I comma jth node. So my counting has to use two variables now, I and j. So this is t of I comma j, and if there are n nodes in each direction in x and y, then I have n square unknowns. But the principle remains the same. My governing equation is d2t by dx2 plus d2t by dy2 equals 0, which when I discretize will give me ti plus 1 comma j plus ti minus 1 comma j minus twice of ti comma j divided by delta x squared. What is happening here? What is happening here is that I am looking at the neighbor to the right, the neighbor to the left, and where I am. Do you follow? Ti plus 1 comma j is the neighbor to the right, ti minus 1 comma j is the neighbor to the left, and so on. This is d2t by dx2. As far as d2t by dy2 is concerned, that would be ti comma j plus 1, the neighbor above, plus the neighbor below, I comma j minus 1 minus t of I comma j divided by delta y squared. All of this must be equal to 0. I will write this equation for every point inside the body. The equations from the boundary nodes will come from the boundary conditions, and I would have written n square equations in n square unknowns. Okay, and you can see that the scale of this problem grows very rapidly. If n equals 100, then in a 1D problem I have 100 unknowns. In a 2D problem I have 10 to the power 4 unknowns, 10,000, right? And in a 3D problem I have 1 million equations in 1 million unknowns. You might think that's a big problem, but it really is not. It's very easy to solve 1 million equations in 1 million unknowns. These days, with computational optimization and all that stuff, this is not a difficult task at all. This can be done within a few minutes in most cases. Okay? What I have presented very briefly is called the finite difference method. It was the first numerical technique that was proposed and developed. It is also mathematically the simplest to understand. In addition to it, there are two more cousin methods, the finite volume method and the finite difference method. The finite element method. As I said, finite difference is the simplest, but it has its own limitations. For example, here I need my nodes to be defined along the x and y directions, right? What if my geometry has a hole in it? Or what if I have a really weird irregular geometry? Then I will not be able to define my nodes in a regular in a regular orthogonal fashion, right? It is important in that case for us to be able to solve problems where the nodes are located arbitrarily. The nodes could be located wherever you want and you want to solve the problem there. When that happens, it is usually the finite element method that is most effective. And so most software tools these days, software simulation tools, are either based on the finite volume or the finite element method. And as I said, the good news is that most likely, unless you're working in a very niche area, most likely you don't have to write your own code to do any of this. Simulation tools these days are advanced enough for you to be able to even tell them what equation you want to solve, right? And then whatever physics it is that you want to capture and solve, they are able to solve it for you. Okay? Any questions so far?
So is it all about the rectilinear heat flow you are mentioning?
Yes.
Is it a rectilinear flow?
It is, yes. So the equations that I wrote in the previous slide
Yeah.
were for one-dimensional flow,
It's for only one.
only one dimension. These equations are for two-dimensional flow
That is for machine.
in x and y directions. Exactly. I can similarly extend it to 3D, where heat can flow truly in any direction that it wants.
It forms like because I am very quite new to.
Yes.
I am not like.
Yes.
What? Especially for heat flow. Right?
Correct.
We are working on some materials to kind of.
Yes.
It's quite interesting fields.
Mhm.
That's what I asked.
Sure.
Okay, elementary one. That's it.
Absolutely. In the end, after you solve all of this, you will get a two-dimensional temperature map, a contour map,
Until.
right? In fact, I will show some of that in the research seminar that I will give, where we solve such problems with complicated geometries. Okay? Any other questions or comments? Okay, so what I would like to do is to, let's see, is there anything else that I want to do here? I just want to make a comment here that a number of transport processes are governed by similar equations. For example, heat transfer, mass transfer, electrostatics, to some extent fluid mechanics. In general, fluid mechanics is a lot more complicated, but certain problems in fluid mechanics follow similar equations. I will add a few more which you may not be aware of. Ecology. A lot of problems in ecology are governed by similar equations. So for example, if I have a large space, a large city for example, and if I introduce some invasive species into that state, I introduce, I don't know, dogs or something like that. How will the dog population grow as time passes? Some of those dogs will go here and there, they will reproduce, new dogs will be born, some dogs will die, you know, they will be eaten up by some predators and so on and so forth. Some will leave the state. The dynamics of population growth is governed by very similar laws. Okay? Ecology, drug delivery, even the stock market. There are people who model the dynamics of, I see a lot of smiles, the dynamics of the stock market using diffusion equations. And I can tell you this from my personal experience. When I finished my PhD, I had friends who had done extremely hardcore mathematics related to fluid mechanics, who went and worked as investment bankers for the top banking companies in the world. They did not know anything at all about money. Okay, all they were very good mathematicians, and they were picked up by the best banks in the world because the mathematics is exactly the same. Anybody who can solve fluid mechanics problems can solve almost any other problems in the world. Okay, and so you learn one thing, you become capable of solving a lot of other problems as well, and we will see that that is exactly how these simulation tools are designed as well. Once a company like ANSYS figured out how to solve fluid mechanics, they said, okay, let's develop a tool for stress analysis. Then let's develop a tool for heat transfer or chemical combustion or whatever else have you. These equations have a very common thread passing through all of them. You learn one, you've learned them all. Okay. So what I will do in the rest of this, rest of today and the next seminar is that I will give a demo of a typical numerical simulation tool, and we will solve some very simple and then maybe a more complicated problem tomorrow in order to demonstrate how numerical simulation tools work. Okay. My goal is not to teach you everything about numerical simulation tools, but that is certainly a skill that you should learn while you are still a student, for a couple of reasons. One is you have time right now, right? Secondly, it's a very good skill to put on your resume. When you graduate and look for jobs, this is something that companies are very much looking for, because as I said, most companies don't have the time or the capability to do mathematical analysis like we are teaching to you all, right? At the end of the day, it boils down to being able to solve problems using numerical simulations. It's not a big deal to be able to solve problems using numerical simulations. You just need to do it a few times and be able to understand how the thing works and so on and so forth. Okay. And also in academia, as a student, you probably have access to ANSYS and other simulation tools free of cost. You'll realize that once you graduate and are out of this cocoon, that ANSYS will actually ask you money to be able to use their license software tools, and it is not an insignificant amount of money. It is a good amount of money. Okay, and therefore, since you have access to those tools right now as students, you might as well learn it now rather than later. Okay, so what we will do is that we will switch gears here. Yes. There you go. All right, so let me close this, and this is the front interface of a simulation tool called, a family of simulation tools called ANSYS. ANSYS is one of the pioneers of numerical simulations, and they are now a fairly large company, and they offer a bunch of different tools depending on which tools you have licenses for. This list can go on quite a lot, but right now I am doing, for the purposes of this demonstration, I am using a tool called CFX, which is a computational tool for heat transfer and fluid mechanics. All right, and the way this flow will work is very streamlined. It says, tell me the geometry. Oops, where is my mouse? There. Tell me the geometry. After that, help me mesh the geometry. When it says mesh, it basically refers to that process of breaking up the body into a number of nodes, right? So ANSYS will ask you, how many nodes do you want me to put? Where do you want me to put those nodes, etc. After you've taken all those decisions, then you will go to setup, where you will basically tell ANSYS all the information it needs to define the problem. You cannot possibly solve the problem, or ANSYS possibly cannot solve the problem, if it does not know what material the body is made up of, right? It cannot solve the problem if you do not tell it what the boundary conditions are. So you have to properly define the problem and communicate that to ANSYS in a certain way that it understands. All of that we will do under setup. And then ANSYS will say, okay, now tell me, how do you want me to solve this problem? What kind of accuracy are you looking for? How much computational time you have available for me, and so on. There are a few choices of the different types of solvers to use. After you specify all of that, then ANSYS will go and actually solve the problem. It will try to hide most of the mathematics behind the scene, but I will show you where to go to look at that mathematics, because you want to verify that things are working as you expect them to work. And then finally, we can look at some pretty pictures, color plots of temperature distribution, contour plots, etc., to be able to visualize what the temperature field looks like. So this is the standard process, the standard flow of the numerical simulation process. we of course always want to start from the geometry. I cannot mesh it or I cannot provide it the material information unless I have the geometry done. So let's start from the geometry. So I will right click here and open up a new window which is already open here. So here is my canvas. This is my open canvas. I can build whatever I want here. I can create any geometry of interest to me and we can go from there. Okay. So here I can say look at, and I can create a sketch for a circle. And this is a two-dimensional sketch. I can specify the diameter of this circle. 20 is good enough. Do I have a keyboard? Will this work? Okay. Until that I can open this and use the keyboard there, right? So I can say 20 meters and then I can go. Okay, all right. Then I can go here and say create, extrude, I can select my sketch and I can say please extrude it to 10 meters. And when I say generate, it would have created this cylinder for me. So this is how my cylinder looks like. Okay. This is a very simple geometry, of course, and so I was able to create the geometry in this body. I can do a little bit of geometry development inside this tool, but for more complicated geometries, this also makes it possible for us to import an external file. So if your geometry is available in SolidWorks or CATIA or any other any other CAD tools, you can always import it into this environment. Okay, I can do. Let me do one more thing here just for our demonstration. Let me create one rectangle. And then create one more extrusion using, what happened to my rectangle? Oh, it's become a part of that sketch. I wanted to okay. Oh,
This work here over here by looking at it. You directly do.
will it help to close this? It's working, so let's go on with it. So actually I made a mistake. I should not have made this square a part of this sketch. So to fix things, I'm going to delete a few things and sort of restart. Let's just start from scratch. So here is my XY plane. I will look at it. I will create a sketch, a circle of whatever the radius may be. "16" is okay. And then I will create a new plane. Sorry, I will extrude this first. Sure, this looks good. So I've created my geometry. Let me create a new plane. This plane is from the face, from this face, look at this plane and create a new geometry of a rectangle. What I'm trying to do is to make a hole in this cylinder. So for that I'll create an extrusion based on this sketch, and instead of adding material I will say cut material. And you can see that I now have a hole in this cylinder, right? So I can do these itty bitty geometries inside, and if the geometry is too complicated for me to do, you can see that even making a simple geometry like this took quite a bit of effort, right? If I have a more complicated geometry containing multiple materials and so on, then it's probably not feasible, practical to do this inside, but I can always import the geometry from some outside simulation tool. So having done this, I think we are ready to leave from here. I'll freeze this and I will exit from here. So now there is a green tick next to the geometry, which means that ANSYS says, good, thank you, I know the geometry that you want me to work on. Next, we need to provide information about how to mesh this geometry, how many nodes to provide in the geometry, and where to place the nodes, etc., and so on. And if you're too lazy, you really don't want to do even that much, you can simply update the project, and ANSYS, based on some default values, will create the mesh itself. Okay, so let's just wait maybe less than a minute or so for it to create the mesh of interest to us. Okay, when that process is complete, this will get converted to a green tick, and we will know that we are ready to move forward. So one of you were saying that meshing is a problem. And which one is this? Okay, all right. Let's hope it works. It will, I think. It's now starting to do the meshing, and it's done. The meshing is done, and I can now open the setup, and I can edit the setup because I want to provide it information about the material and so on and so forth. So here is my geometry, and this is how the mesh looks like. Yeah, it has about maybe 10 steps in the z direction and maybe about 10 steps in the radial direction. And this really is a very coarse mesh. If I want to have confidence in my results, I really would like to have a much finer mesh. Much finer mesh, in fact. I will not do that for now to save on computational cost, and let me just do the demonstration using this alone. Okay, so here I am now ready to define what things look like. I'm going to try and I'm going to try and do this without the use of a keyboard, okay, because we ran into trouble when we opened this, okay. So let's see. I'm going to go inside and I'm going to say this is a solid body and the material is, say, copper. ANSYS by itself knows of only a few materials by default, but if you want, you can always insert a new material within. Oh. No, this is going to be a problem. I don't know why this is happening, but all right, sounds good. Thank you. So here is my material. I need to define boundary conditions in this material. So I will say insert a boundary and I can call it the hot boundary, right? This boundary is, say, this. So the curved surface, some heat is entering this body from the outside and I can say that this is at, I need to now define the boundary condition. Those of you who are familiar with heat transfer know that there are three types of boundary conditions. Either you define the temperature, or you define the heat flux, or you define a convective heat transfer coefficient, right? Here, let me just define the temperature alone. So the temperature here is 10 Kelvin. And when I say 10 Kelvin, I don't literally mean 10 Kelvin. 10 Kelvin will be a very cold temperature, right? Here, temperature really refers to temperature rise above ambient. So I'm saying that the curved surface is 10 Kelvin above the ambient temperature, okay? Please don't understand this literally. It doesn't mean literally 10 Kelvin. It only means 10 Kelvin above ambient. All right. So I will get out of this. I will then also define one more domain, one more boundary called cold, and that could be this perhaps, and the temperature there is going to be 0 Kelvin. So this is at ambient temperature. And any boundary that I do not define will be assumed to be adiabatic. No heat loss through all other boundaries. So basically heat will enter inwards and it will leave from the top is what we expect to see. Okay? I can go to analysis type and make sure it is a steady state simulation, and under solver control, now this is sort of the nuts and bolts of the simulation. Okay, it is asking you how many iterations to do, it is giving you a choice about the type of residual, it is a lot of things here that you don't really know what to do about. As an early user, it is okay for you to just leave the default values, but as you become more and more of a sophisticated advanced user, you've got to understand and learn what each of these things mean and do. Roughly speaking, the lower the residual, the higher is the computational cost, but also higher is the accuracy. So I have learned through the years that this number that ANSYS gives you by default is actually too small, or rather too large. I need my residual to be much smaller, and I need the number of iterations to also be at least 200. Okay? With that, we are ready to solve this problem. There's a few other advanced things that I will look at tomorrow when we come back to ANSYS and solve a problem related to lithium ion batteries. Okay? For now, I think we are ready to proceed. I will close this because I have told it everything I needed to tell it. Just one little thing is to give it a suggested initial value, which will be helpful in calculations. And I can close this. And now I'm ready to solve the problem. yes, thank you. So I hit the start run button, and now it's doing all the mathematical mumbo jumbo in the background without really telling me much about it, right? So all those setting up the number of equations that we talked about and solving those equations is now beginning to happen. And it is plotting the residual. Oh, and it happened very quickly. My residual criteria was reached within a few iterations. Actually, it finished 200 iterations very quickly, right? It was so fast because my mesh was actually extremely coarse. If something like this happens, I always go back and make my mesh finer. I don't want, I mean, I can afford to spend more time to solve this problem, right? It happened in less than 1 second. Even if it takes 1 second, 2 seconds, 5 seconds, 10 seconds, even a minute, I can afford to spend that cost in order to get better accuracy, right? And then there are some other things here. For example, you should always look at the residual criteria, the imbalance criteria. You see, it is telling you that the total imbalance in the problem is, pretty much zero, which tells you that you have solved this problem very accurately. Okay, and this happened so quickly because this problem was extremely simple. It was perhaps the simplest problem one could think of, right? Any problem that is more complicated than that will take some more time and effort to solve. Okay, I'm not trying to trivialize numerical simulations here. My students certainly do some numerical simulations in ANSYS that routinely take several hours, sometimes more than 24 hours to finish. Okay, all right. So in the last few minutes, I just quickly want to show the results. Where I will create a contour plot of the temperature distribution in the entire body, and that will look like a beautiful temperature color plot of the problem. See, the temperature is the highest around the curved surface, and the temperature is the lowest on the top, and everywhere else the temperature is what it is. Okay, you will see that there is some problem here at the boundary between the two boundary conditions, and that is mainly because our mesh was extremely coarse. Okay, and you can create all kinds of contour plots, two-dimensional plots, line plots, and analyze a bunch of other things using this interface. So tomorrow when we do the next tutorial, I will take up a real life battery problem, and we will solve that battery problem using CFX, and then we will be able to ask a lot of questions to the simulation. What happens if the battery is twice as large? What happens if you flow more air over it? What happens if you do this or do that? What happens if the material of the battery changes, right? We were saying earlier today that if the thermal conductivity can go up, then it will be of a great benefit to the temperature distribution. We can ask those questions to ANSYS and say, look, what if I have a material that has twice as much thermal conductivity? How will the temperature change? Okay, we'll do all of that tomorrow, at the end of the day tomorrow during our third tutorial. Okay, so for now we'll finish here in the interest of the other seminar, and we'll go from there. Okay.